Hello everyone, welcome back. Thank you for attending. Let's talk a little bit. Let's keep talking about the dot product and cross product. And we talked about the dot product quite a bit and drew numerous conclusions. So that's good for us. We can use that for future reference and for future work. As we talk about the dot product and the cross product, let's go to the cross product and let's say a couple things. Let me introduce something once again from some of the brilliant work of Munham and Foulis from their calculus book, I think entitled Calculus, from 1984. So Munham and Foulis, we're going to use some of their brilliant work, some of their brilliant research yet again to look at a few things and then kind of come back to some of the conclusions that we drew that we find looking at Munham and Foulis and their work. We're going to come back to it somewhat later, hook around, and then draw some interesting conclusions. But right now, I'd like to put some of this stuff up front. It'd be nice if the blackboard space was unlimited rather than being limited. But you know, it's not unlimited space. So I'll put as much up there as I can. We'll talk a little bit, and we'll go from there. A lot to say here. Well, in general, guys, let me try to use a few things here. And even here, they're using the letter theta up here. Well, you can use any letter. You use the letter phi. I almost wanted to go against what, at least some of the notation, just a little bit of the notation that Munham and Foulis used. I could have called this one phi and called this one down here between vectors A and B. That angle usually they call theta. It doesn't matter. If this is theta right here, then this right here is phi between the two. Okay, that's not a real big deal. Essentially, guys, when they talk about the cross product in and of itself, what is it defined as? If you have a vector A and a vector B, and I'm not going to get into all the special case scenarios. The overwhelming majority, if not all of the special case scenarios that maybe you could think of are rather trivial. We already kind of know what the conclusion is going to be regarding something like that. So we're not going to make a big deal out of it. We're going to put both of these, they're not going to be collinear. Any two vectors that start from the same origin, we've already said that in prior discussions, are coplanar. When two vectors start in three-dimensional space, when two vectors in three-dimensional space, when two vectors start from the same origin, those two vectors are coplanar. Now you got to find a vector that's perpendicular to them and has a certain attribute. Well, there's a lot going on here. This thing called the cross product of A vector and B vector there's a lot you can say here. I mean, we'll see what the exact conclusion is, but this vector, the cross product of A vector and B vector, is going to be a third vector that is perpendicular to the two vectors in a right-handed fashion. So the order in which you do the cross product does matter, and we'll see what we can say on that. Let's put it, for example, let's say this is this eraser right here that I have is A vector. And this vector that I have right here is B vector. If I did the cross product of these two vectors, I always go from A vector to B vector. I roll the fingers of my right hand in the direction in which the palm is pointing, so to speak. Roll the fingers of the right hand in a right-handed fashion, and my thumb will be perpendicular to the plane determined by these two vectors, and that is the direction of the cross product. Well, okay, there's a direction. What about the size of the cross product? The size of the cross product is the angle between them, the sine of the angle between them times the product of their magnitudes. So it's a little bit easier done than said. Frequently, they use theta as the angle between A and B. Here I use theta right here, following closely the brilliant work of Munham and Foulis. that's okay. Let's just use another angle. Let's say the angle between these two is phi. Anywhere. Now we said, if there is a vector, say a vector, and there is a vector, let's say b vector. It doesn't have, they orient any way you want them oriented, guys. Let's say that's b vector. And this is the angle phi between them. A vector cross b vector is a vector. You take your right hand and roll your fingers from a vector to b vector, and whatever direction your thumb is pointing is the direction of the cross product, is the direction of a vector cross b vector. Here's a vector, here's b vector, a vector, b vector, do the cross product. A vector cross b vector, boom. It comes out this way, and coming out this way is the direction of the cross product. Any two vectors that start from the same point of origin are coplanar. So I can just simply take this blackboard as the plane that contains these two. They don't have to be right here looking right at you. They could be like this, like that. You know, they could be everywhere. If I'm talking about these two vectors, a vector cross b vector, they could be oriented like this, like this, like this, like this, like this, like that, like this, like that, like this. So the vectors are oriented, as long as they have the same origin, they're always coplanar to some plane that contains both of them. And when you do the cross product, you apply the right-hand rule that I just showed you, and you get the vector, and you get the vector a vector cross b vector. As far as direction is concerned, what else do you need to know? Well, the magnitude of this thing is equal to the magnitude of a vector times the magnitude of b vector times the sine of the angle between them. That's the magnitude of it. The direction, I just told you, it's perpendicular to the plane containing both vectors. What does that mean? It's simultaneously perpendicular to both vectors in a right-handed orientation. There's only one other vector that's as big as that and is perpendicular to both those vectors, and that's the vector that goes into the blackboard, to the other room, let's say. It goes that way. It goes bam, not coming out this way toward you, but that way away from us. Yeah, but it's not right-handed. If I go A cross B, my thumb points out this way, this is the only one that works. Now, if it was a left-handed cross product, where you would do, with the left hand, you take the fingers and roll, A vector cross B vector with the left hand, boom, yeah, it does go in that way. That'd be a left-handed orientation. There's other ways they talk about left-handed orientation. That itself could be a little more confusing than helpful. I go into the documents that I have here, the 3 documents. Much of what I'm going to say is in those 3 documents, not necessarily in the order that I'm doing this stuff, but it's all there. And so you're going to see it in the film and or you're going to see it in the documents as well, you guys. So this is the situation as far as that's concerned. So this A cross B, if you wanted to, I don't know, if you wanted to kind of say it this way, I get here's phi. This is B right here now. Didn't want to do this, now I'm doing it, but that's okay. I mean, this thing, what is it? Well, it's as big as A times B, the magnitude of A times the magnitude of B times the sine of phi, and I'll put like a unit normal vector, the unit normal vector that is perpendicular to A vector and B vector simultaneously in a right-handed fashion. Well, that's interesting. That's basically what's going on here when we do this stuff, guys. Now, I'm going to show you a way that I sort of looked at it. I'm sure I'm not the first person to have looked at it in the way that I'm going to tell you shortly. Not now, though. I'm going to keep talking a little bit more about this. But I'm going to show you a way that I kind of looked at something. I'm sure I'm not the only person to have looked at it in this manner. And the way I kind of did it was, I said, okay, let's draw some conclusions, and then let's sort of throw the dice. let's take a couple educated guesses at this and see if it's going to work. Well, luck's kind of a weird thing. You get it sometimes, you don't get it other times. So turns out this actually worked out okay when I had done it. We'll talk about that in a bit. Munham and Foulis, the way they did it, is more intuitive, and there's no guesses that you got to make. So in that regard, their job is better. They did a better job than I did. We draw the same conclusions. I luck out with the guess. We'll talk about that a little bit. But what they're doing is really excellent. Now, how do they talk about something? And like I said, I'll introduce some of what Munham and Foulis had done, and then after we'll kind of hook around and mention them again. But let's get this in our mind and look carefully, I guess, how we're doing some of this stuff, you guys. Munham and Foulis approached the discussion of the cross product from the perspective of using the dot product and the cross product to find the volume of a box. A box that's analogous to a parallelogram. I think they call it a parallelepiped. It is a box. It could be a rectangular box where there's 90-degree angles everywhere. It could be a square box called a cube, which is a special kind of rectangular box. Or it could be some kind of rectangular box, generally speaking, that's been sheared over, that's experienced a shear force, so to speak, and has kind of gone sideways, kind of something like this. It's not necessarily a box that's got 90 degrees everywhere. It's just bam, you kind of sheared it over to the side, and you got what you got. Well, I'd like to find the volume of that general parallelepiped box. Volume is equal to V. Tell you what I'm going to do. You've got A vector, you've got A vector, you got B vector. I introduced the phi here, so we kind of just have it for us. And there's C vector right there. I'll tell you what I'm going to do. We know that if you find the area of any base where that base area is always the same regarding some sort of perpendicular, when you're taking perpendicular cross sections, that base area is always the same. So if you multiply that base area by the distance that it is being moved, even if it's being moved sideways, if you are moving a base area in a direction where you take cross sections and that area stays the same, then the length of that movement of that base area, the length of the movement of the base area, call it H, height H, and the base area itself down here, the volume would be A times H. Well, I already kind of said, as far as the magnitude of the cross product is concerned, it's the magnitude of A times the magnitude of B times the sine of phi. Well, wait a minute. Here's the magnitude of A. That's how long it is. That's the magnitude of A. Here's the magnitude of B. That's how long that is. If I multiply the two and multiply by the sine of phi, wait a minute. B times the sine of phi gives you that kind of a height for the base. The height times this base length, A, will give you the area down here. The area down here times H will give you the volume. Well, wait a minute. Isn't the length of C vector times the cosine of theta going to be as long as that? Look carefully. Let's ask the question here. There's a number of ways you can do this. Is really what's going on here. But look at this right triangle here, ladies and gentlemen. That right triangle. If I take the length of C vector, this hypotenuse, and multiply it by the cosine of theta, I get this length, which is H. Well, wait a minute. Isn't magnitude of a vector times magnitude of a vector times the cosine of something, done the right way, isn't that the dot product? Basically, if you find out what this guy is, A vector cross B vector, you get this long vector here called, probably get this long vector, maybe a shorter vector, who knows. But let's, for the sake of just the argument here to see it, here's A vector, here's B vector, cross product, boom. Here's A vector cross B vector, which is the size of AB sine phi times the normal to this in an appropriate right-hand manner. Okay, great. That's just the length of the base. That's just the area of the base. I'm describing it by this big vector here, which just tells me, that big vector tells me the area of this base. True. Now multiply this area of the base by the height. Well, that ain't the height. You got to get cosine theta on there. I'll tell you what. Take C vector, take A cross B vector, do a dot product, and it will indeed give you the volume, which is what? AB sine phi, that's the base area, ladies and gentlemen, times C cosine theta. Wait a minute. Okay, yeah, that's true. AB sine phi is the magnitude of A cross B. A cross B vector is this vector. The dot product with this vector is magnitude of this times magnitude of that times the angle between them. What happens is, let me kind of go over here. There's a lot of stuff written here, guys, obviously. What do you got? You got magnitude of A, magnitude of B, times the sine of phi. That song and dance was the base area. Multiply it by the height, which is C cosine theta. True. What's going on here? Well, this guy right here is the magnitude of A vector cross B vector. And this right here is C cosine theta. So it's the magnitude of C, times the magnitude of A vector cross B vector times that. What does that mean? Well, it means I don't have any room is what the first thing it means, guys. Let me try to find some room here because there's some other stuff I want to talk about. But let me, so you see what's going on here, guys. We got, so basically what's happening here, guys, is you're getting the magnitude of A vector cross B vector, and you're multiplying it with the magnitude of A vector cross B vector, which is just a scalar, magnitude of A vector cross B vector times the magnitude of C vector. After you've done those two, after you've done that multiplication, you multiply by the cosine of the angle between these two vectors. There's something to be said there. Okay, said what we said. What it means is you're taking A vector cross B vector, and you're dotting it. Look, isn't this a dot product, guys? It's an elaborate dot product, a little different than what you've seen. But I said there is a magnitude of A vector cross B vector. The magnitude of A vector cross B vector, well, A vector cross B vector is a vector. It's perpendicular to both A vector and B vector, and it's got the size, magnitude of A times magnitude of B, times the sine of phi, phi being the angle between A and B. Yeah, it's the size of it, and that's actually the base area. Multiply the base area by the height, which is C cosine theta, you're there. You're in business. So what happened here? That's wait a minute, magnitude times magnitude times cosine of the angle between them is vector dot vector. And that's where that's coming from. And that's where that is coming from. And that's where this is coming from. Now, this is a nice geometric figure to look at. The box here is, the orientation of it is very intuitive. You got A vector, B vector, C vector. What if C vector went diametrically opposite to where it's going now? That wouldn't be a right-handed orientation. You'd be going A vector cross B vector. You'd do this. You'd go A vector, once again, you would go A vector cross B vector, bam, it shoots up this way, but the C vector is bigger than 90 degrees from the A vector cross B vector. The theta would be bigger than 90 degrees, which means that the cosine would be a negative number. You wouldn't be getting this, which is what we got initially. You wouldn't be getting this, you'd be getting this instead. You'd be getting something that was in the opposite direction. You'd be getting a negative answer. If this whole thing's a negative answer, if this whole thing's a negative answer and I multiply it by -1, then I get a positive answer. I'd have to put a -1 in front of it. Negative of a negative is positive. I'd have to go -1 if C was pointing in a diametrically opposite direction than what it was initially pointing. You'd be getting the same magnitude box, but it would be a negative volume, so to speak. You get a negative answer. Well, I don't want a negative answer. Well, then go negative of a negative. And then you'd get the positive answer you got there. This would be, they call that, if this thing was oriented this way, they would call those three a left-handed orientation. Because you would get the right answer if you had a left-hand rule on there. Go A cross B, boom, it goes down, and then it's in the same direction as C vector. I don't want to go there. Munham and Foulis in their great discussion kind of talk about left-handedness a little differently than I do. Essentially, it's the same thing. It becomes, if we watch what we're doing, it becomes a little more than a linguistic difference, and it's not really a big deal. So you see in my documentation, it's a little different than that. The big argument here, guys, is you do this, and if there's a nice right-handed orientation, well, this guy shoots up this way, and the angle here is less than 90 degrees, you're okay. If C were there, if C is this way and the theta is less than 90 degrees, if C was going this way, bam, that guy's firing down this way. I don't want to draw it, guys, but it'd be firing this way, and A cross B vector is this, the C would be that way. The cosine of something bigger than 90 degrees is going to be less than 0. The cosine of something equal to 90 degrees is 0. So you want it to be less than 90 degrees, but when it's more than 90 degrees, there's some special cases here, guys. If it's more than 90 degrees, if C was pointing the wrong direction, if it was pointing in a direction that's just not right-handed, that's okay. Then we start doing this. Then we just say, oh, that's going to be a negative answer. Well, that ain't the volume then. If this whole thing right here is a negative answer, then put a negative in front of it, you get the positive answer. That's what Munham and Foulis were doing in their brilliant work. Really just excellent work. So you're looking at it in this manner. So that's it. I mean, this is it. Volume is volume, guys. It doesn't change. Move a base area, any base area you want. There's 6 faces on this thing, man. And if there's all this symmetry, you can move any one of those base areas. I mean, you could use this base area or that base area or the base area coming out at us like this and then move it through a particular distance. The numbers are all the same in a different, well, let's put it this way, the volume is going to be the same. It doesn't look like you're getting the same answer, but you got to get the same answer. The volume doesn't change because of your mathematics. If your mathematics is valid, and Munham and Foulis are brilliant in their presentation here when they do that. They're brilliant with their presentation when they do that. Any one of them is going to work just fine. So in other words, are we saying here A
A cross B. A cross B, bam. A cross B dot C, that's the volume. Yes? True. Now take a walk. Come over to B and go B cross C. Go B cross C. Well, that's going to come out in a kind of a weird way, but it's going to come out. B cross C, that's this area now, guys. Yes. B cross C dotted with A, that's a different age. B cross C dotted with A, that's also the volume. B cross C dotted with A, that's also the volume. It doesn't matter the order that you do a dot product. The order you do a cross product does matter. It'll orient in an opposite direction if you do that. I've already mentioned that. And you'll see it in my documentation as well, guys. Okay. Okay, what about C cross A? Boom. Goes into the board. Here's B. Dot though. The thetas are different. These thetas aren't going to be the same. You're going to have a new H going into the board. B cross, so we do, so what did we do now? Let's see how we did it. Yeah, we said C cross A, and bam, C cross A dot B. C cross A dot B works just fine. If one of these leaves the right hand, they're all right-handed orientation, so all of them are good. So all are good, my friends. We have all of this. True, absolutely true. If any one of these violates the right-hand orientation, then we got a left-handed orientation. And there's a way you can look at it. You can hypothetically move the B out of whack or move the A out of, move the B diametrically opposite to what it was, or move the A diametrically opposite to what it was, or move the C diametrically opposite what it was. I think if you move all of them, I think you go back to a right-handed orientation in a different way. Okay, that's another. But I think if one of them there, we kind of look at it. There's various experiments we can do on this to get it. But for our purposes, let's kind of stay with the orientation we have. The specifics of it, we can find for different circumstances, but we do know something. That if they are out of orientation somehow, let's take, and that can happen with any one of these. Take the C vector and make it diametrically opposite. When you go A cross B, you got this, the C's down here, that's going to be a negative answer. It's going to be the exact same answer in terms of magnitude, but it's going to be negative. They go negative of that and you're fine. Go, if C was down here now, take this cross product, it's going over that way, but it's out of whack. It's going to be the same magnitudes that we were talking about in the past, you guys, but and what the angles are of interest. I got to tell you, here's one thing for sure. If this is angle theta, when you go down here, it's kind of like angle theta. It's angle theta plus 90 degrees. So there is, the angles don't go out the window. I think I spoke rather flippantly earlier. There's going to be different angles, but there's a lot of mathematical association, valid mathematical association, a lot of symmetry. The cosine of the angle is still going to be the same magnitude if you have the right, if you're talking about appropriate orientations with these items. One's going to be, cosine's going to be positive, the other cosine is going to be related to an angle that's 90 more. That's somewhere else when we look at it, and that should be of interest. And that's very interesting how that all plays out. One's going to be, the angle set up in such a way that you're going to be getting the same magnitudes. Nothing bad happens that way. So what do we say here? Say A cross B, the C's here. It's off. It's going to be a negative answer. Well, they'll go negative of the negative. And that's what I did way over here, you guys. And you're going to be playing the same game throughout on all of these. Go B cross C, that's there. The C's down here. B cross C this way, it's off again. How far off? It's it's really close to what the other one is. It's going to have the exact same magnitude, but it's going to be a negative sign. So it's going to be a negative answer. So if I want to get the volume, I got to put a negative here. The same thing here. You go C cross B. So let's see. C cross A rather. I'm sorry. So you got the C came down here. C cross A. Bam! It's flying out in a way that it didn't fly. It doesn't fly into the vectors. It flies away from the vectors. But the magnitude of the cosines associated with this flying away, the magnitude of the cosines are equal. One's positive, one's negative, and you're getting this. And like I said, this happens across the board, guys. If you set this up in such a way, we're not worried about. I mean, I could play a whole bunch of games here with these. I set these up in, a number of ways that they're all opposite or all oriented. That's not a problem. The orientation is locked in to one of two realities. Always, no matter how I mess with those three vectors, always, the three vectors with which I am dealing, how I plan to do my cross product. Once I pick a way I'm going to do a cross product, I can do that around the cycle and get something like this. I can do this around the cycle and get something like this, you guys. This says or, so it's one or the other. I can go around the cycle and it's either, there's an infinite number of ways you can orient these, how you're doing stuff. I guarantee you, A vector, B vector, C vector, they are how I'm choosing. If I'm choosing to take a vector A, a vector B, a vector C, and I'm going to do A vector cross B vector dot C, that's how I'm finding the volume. Once I go around, kind of use the baseball scenario, around the horn, once I go around, guys, in the right way, it is right-handed, and that's the end of the story. Or it is left-handed, and that's the end of the story. So that's the big that's the big thing. That's where Munman Foulis we're talking about this thing, you guys. And as we said, that's essentially what we had said. So what does that mean? It means a lot. It means all of this equals all of that equals all of this other one. All of this equals all of that equals all of this other one. They're all equal to each other. These are equal. Yeah. This, and this other one, they're equal too. If they're all equal, set them up as an equation and multiply by -1 on each side, and this negative leaves, and you got this, which is the exact same thing as that. That's important. Doesn't matter the orientation. If you set this up in a reasonable manner mathematically, right-handed or left-handed orientation, that's what you're getting. And that's important. That's where Munam and Foulis and their brilliant work had gone. From there, they were able to draw various conclusions. I'm going to go kind of like in a little bit of a different direction when I'm doing some of this stuff, but I just wanted you to see this stuff when we look at it. All right. Well, I tell you what, we'll come back to this. We'll touch on it again. We're going to see a lot of stuff. Let me see exactly what I want to say here, guys. So many orders you can take to do this. There are some really just wonderful conclusions that get drawn when we're doing this stuff, guys. Well, I'm trying to argue a little bit with myself where to go with this. All right, guys, I'm just debating here a little bit what I want to say. let me stay with where they had gone, guys. I thought they did. I mean, they've done a great job. We've gotten to this point. Why not stay with it? And then we'll kind of go the way I showed it. Again, I know I'm not unique in having done what I've done to show what I've shown there, but I think there's another interesting way to look at this beside Munham and Foulis. Let's stay with Munham and Foulis, and let's take a look. Let's take a look at what we have here, and let's see. I mean, based on everything that we said, let's see what kind of conclusions we can be drawing, you guys. So, just a lot of debates here, guys, where I want to go with this, how I want to do this. Luckily, like I said, I always forget. That's why I always repeat the stuff. I always forget that you have the fast forward feature and the reverse feature for the film. So that's a little bit better that way. All right, let's take a look at it. We've got this. Let's stay with these conclusions. We've got them. You have access to it. The documentation is going to have everything that I'm saying. It's going to have it almost for sure in a different order than I'm showing it, but it's all there. It's all there for you. Let me start erasing some stuff here, guys. All right, let's stay with Munham and Foulis, I guess. See exactly how I want to approach some of this stuff, guys. For the all scenarios, guys, that we talked about, we got. Let's talk. I mean, again, I'm still debating what order I'm going to do some of this stuff, but let's stay with it and see what we can say here. We know, we've come to the conclusion. We've said some stuff. Let's say it again. And again, notice, I mean, let's talk when we do this, actually. There is an arbitrary nature on how you call a vector a name. True. Once you call it, though, you got to be consistent. If you stay consistent with the vectors that you're calling, you're always talking about volume, and you're talking about a positive volume or a negative volume, but they're all, if you're talking about a negative volume, ladies and gentlemen, if you're talking about a negative volume, so to speak, they're all negative. Multiply by -1 and you get the same answer. If you're talking about a positive volume, they're all positive, so leave it alone. In both cases, if you multiply by -1, you get this, all of this. If you don't multiply by -1 because you don't need to, you still get that. That was kind of the thing. It's a universal conclusion for all scenarios, whether negative volume or positive volume, so to speak, because when we multiply, we get this. Okay, I mean, we've said that. So, continuing with much of the brilliant work of Munham and Foulis, the distributive law associated with the cross product will be established. We will establish that for any vectors in three-dimensional space, that this holds. So let's talk. I mean, we get to here. If I do it for this, once you draw the conclusion, you guys, you'll kind of see that the conclusions are universal, independent of how you prove something. I can prove something in a different manner. If I'm drawing the same conclusions, then the same conclusions are correct in both instances. Okay? So you don't need to do, I mean, once we see what happens in one of these scenarios, now with Munham and Foulis and their brilliant work, once we see that, when we look at what I've done, the same application obviously is going to work because I'm drawing the same exact conclusions. We'll get to that when we get to that. We will establish that for any vectors in three-dimensional space, so we said this, let me just say a couple things. Okay, we got this. We said we will establish that A vector cross B1 vector plus B2 vector plus B sub n vector we're going to say, now again, the order does matter with a cross product. I already went there with everybody on that one. It matters in the sense that you're going to get the exact same magnitude vector, but a vector oppositely oriented, or oriented in the exact opposite direction from where the other vectors are oriented. We're going to get this, and we're also going to see that on the other side of that, and we can see, I'll show you what, I kind of did something a little different here. I'll show you. I mean, it's just a little more writing for me on this, but that's all right too. Looks a lot like what we were doing with the dot product, you guys. Analogous conclusions get drawn. You'll see completely analogous conclusions get drawn. Completely analogous conclusions get drawn vis-a-vis the cross product when compared to what happens with the dot product. There are two different realities. The dot product is a scalar. The cross product's a vector, and the order that you do the cross product matters. Magnitude won't change regarding if you change the order, but the direction of the resultant vector does change. However, didn't we do the distributive principle with the dot product and we saw a lot? Sure. In a completely analogous fashion, we're doing the same thing with the cross product as well. So let's see what we have here. So we got this. All right, it looks awfully familiar. I told you there's an analogy here, and generally for any m and n that are natural numbers, we're going to have this. Let me show you. Here's m. M not the same as n necessarily. Could be, but it doesn't have to be. It's a general statement. Equals, and here we go. Basically, you're taking the A1 and doing cross products all the way across. Then you're taking the A2 and doing cross products all the way across. Then you're taking the A3 and doing cross products all the way across. That's the same as reversing the two. Take this guy, put him over here, and this guy over there. You're going to get the same magnitude vector, but oppositely oriented. And that'll follow from the conclusions that it follows anyway, guys. It follows from the conclusions that we drew earlier. That means all of these, I'll show you in a second. So we got, let's see right here, guys. Okay. Got that. And, well, look. I think we get the picture. Right. And plus dot, dot, dot. It's going on all over the place. I drew it a little differently in my writing. Let me see here, guys. I'm going to give myself a little bit room because it's not going to look too good if I don't give myself too much room. I think you see where I'm going, though, guys. A sub m cross B1 plus A sub m, these are vectors. Plus dot, dot, dot. Plus right here, actually, I'm sorry. A sub m and there you go. So what's going on here? Well, we talked about this and how it plays. And we talked about this. I mean, there's a lot of other conclusions, guys, that I'm more than I've drawn actually, but these are pretty major ones. You saw that, and we said, man, we could take this and take it to a really general level, and indeed, you're looking right at it. Yeah, what's going on here? Well, first of all, there's ways, if we already know a lot, more than and we're going to know a lot more, I think. But we do know a lot. We're saying if this reality is something, and it is, first of all, don't let it scare you too much. How did we add vectors? How do we always add vectors? Yeah, I mean, that's probably the best way to put it. When we were dealing with the dot product and we wanted to do distribution that was taking place associated with the reality of the dot product, when we added, I don't know, a quantity composed of 1 million vectors in three-dimensional space,
the x component, the new x component is going to be the sum of the million x components that are there. The new y component is going to be the sum of the million y components that are there. And the new z component is going to be the sum of the million z components that were there originally. And you got just one vector. There's a new a sub x, a new a sub y, a new a sub z. You add a whole bunch of vectors, you just get one vector, guys. Makes it easy. This right here, as convoluted as it is really one vector when you get the resultant. The resultant of the addition is one vector. The resultant of the addition over here is one vector. The cross product between two vectors is something, obeying the right-hand rule and giving you the cross product. What is the magnitude? Well, it's the magnitude of all this. It's the magnitude of all that multiplied together. It's the magnitude of the vector composed of all this. The one vector you get from all this, the one vector you get from all this, the magnitude of this vector, big vector, the magnitude of this big vector, times the sine of the angle between the two big vectors that you got. Now, what does that mean? Well, what's the angle? Well, the angle's different. You got to find the angle. There's a lot you got to do, but we can do it. Magnitude of all this times magnitude of all that times the sine of the angle between them, and it is perpendicular to both these vectors. The resultant vector, the cross product, is perpendicular to this resultant vector and that resultant vector, and it has magnitude of this resultant vector times magnitude of that resultant vector times the sine of the angle between the two resultant vectors. And it's perpendicular to both those. Yeah, okay, sure. Got another question to ask you. Yeah, this is what it is. I'm claiming it's that. If you take the exact same megavectors, this megavector, and put it over there to the far right, and take this megavector and put it over to the far left, and do the cross product, it's the exact same magnitude, only diametrically opposite. The vector that you originally had is whatever it is. Let's call the cross product of these two huge vectors, we'll call it C vector. If you reverse the order of doing the cross product, you're going to get negative C vector. Exact same size, just diametrically opposite. How can I do that? Well, I guess you take all of these vectors, and multiply the whole quantity by -1. Really? Okay, if I multiply this whole quantity by -1, there's a -1 in front of all these. There's a negative symbol in front of all these. True? Yeah. But A vector cross B vector is equal to the opposite of B vector cross A vector. So if this guy right here is C vector, then this guy right here is also C vector. C vector is the opposite of B vector cross A vector, because A vector cross B vector was equal to C vector. What does that mean? Well, why don't you multiply by -1? B vector cross A vector is equal to negative C vector. All of these guys multiplied by -1 and added together are the exact same magnitude vector, only oppositely directed in three-dimensional space. If you multiply all of these by -1, it's like multiplying the whole thing by -1. Yeah, the whole thing multiplied by -1. If this is C, this is negative C. If this is C, this is negative C. If you multiply that entire big vector by take that whole quantity and multiply by -1, you're just oppositely directing the vector. What does that mean? That's the same as all of these multiplied by -1 and added together. That makes sense. It's like me saying to you, 5 plus 10 plus 15 is 30. Yeah, why don't I multiply that quantity by -1? That's negative 30. Well, how about I distribute that quantity -1? -5, -1 times 5, -1 times 5, -1 times 10, -1 times 15. I got -5 plus -10 plus -15 is -30. So you multiply by a negative, bam, it comes in. It'll change it by any scalar. Okay, there's a lot going on here, guys. This is a really important conclusion.
Well, I haven't drawn the conclusion yet. I'm just telling you it's an important conclusion. There's m rows and there are n columns in this one right here as we look at it. So you look at it. There are m rows. Really lends itself to like determinants and matrices and stuff. It's not an accident. M rows M rows and there are n columns. Now, there's a lot to be said here. I mean, I'm kind of going in a, again, I'm trying to make a little, I'm going against the way I kind of, just in terms of order, you guys. This is all valid. There's nothing wrong here. There's a lot you can say to get there. Okay, so Munham and Foulis get us to where I'm going to go at another point. I'm not going to have to do some of this stuff again when I show it quote unquote my way, and it's certainly not my way, I'm sure. But it's somebody else has done it. I just can't remember seeing it, but it's there, I'm sure. But Munham and Foulis, let's look at their way of kind of, okay, we said all this. I say here, Munham and Foulis, again, their calculus book, 1984, great book. Munham and Foulis brilliantly get it, Munham and Foulis brilliantly get us to the basics that get us to the exact same conclusions that we need to go. Once we get the basics, then we proceed by induction to all the generalized cases of the distributive property and everything that we saw. Once again, see and prove. So let me, again, I'm going a little bit, I'm following a little different order here. Let's talk. I said I said a lot. We've got this. Let me erase this and let's talk a little bit, you guys. Don't want to erase any of it. I told you that. But we got it. You have access to it. And when you see it in writing, it's going to be a different, I go in a different order. I kind of jump around in a little different manner. Conclusions are, the most important thing are, the conclusions are, I hope, accurately, I know they're accurately depicted. Hopefully they're well motivated. Hopefully you can see what's on there, because we are going to draw the right conclusions, no matter how we go about doing this. All right, we know a lot. What do we know? What are we going to say, guys? Look, some stuff really bounces. Really, these conclusions are interesting for the discussion here. Dealing with volume is kind of an interesting thing, man. Notice that a lot of this can be viewed. Well, you're going to see this. You see you've already seen that in your own background with the mathematics. So many ways to look at what's going on here. It's neat how this somewhat abstract concept, a little bit intimidating concept, this cross product, how it's related to volume. And we talked about that in different games we could play. Well, here are the conclusions of the games that we drew. What's of interest here, guys? Well, I got an A, I got a B, I got a C. I got an A, I got a B, I got a C. Hold on. If this is going on as a general rule, regardless of whether the vectors are quote-unquote right-handed or left-handed, regardless of whether the vectors are right-handed or left-handed, regardless of that, we know something here. A vector cross B vector dot C vector is the same as A vector dot the result of B vector cross C vector. Wait a minute, ABC is right here. It's right in front of me. If you take the cross product and the dot product and interchange them, well, let's talk about that a little bit too. You can't really do a dot product. You can't really do a cross product with a scalar. They got to be two vectors. So this whole thing about the way the parentheses are is not as vital as you might think, as long as you keep an eye on what you're doing. I'll just make a long story short here, guys. A vector cross B vector dot C vector is the same as A vector dot the quantity B vector cross C vector. Look, they're right here, guys. If you take the cross product here and the dot product here and the cross product symbol and the dot product symbol, pick them up and interchange them, and then appropriately call this thing, because you can't do dot and dot and then do a cross product. It doesn't make any sense. So make the parentheses go where they got to go. Notice that the dot and the cross can be changed, interchanged. The dot product and cross product can be interchanged. Well, that's important, because Munham and Foulis want to show us something. They say that A vector cross, well, let's go. Now here we go. I mean, this is going to be of interest. I mean, let's leave this here. This plays a role, but not immediately just yet, but it's going to play a role. Okay? Let us see what we got. A vector cross the sum. I'm working toward the conclusions that I was telling you we're going to reach anyway. A vector cross the sum of these two vectors. We already discussed this I don't know about ad nauseum yet, but trust me, by the end of this discussion, you might think it's ad nauseum, I guess. When you're adding two vectors, you got another vector looking just like B vector looked, or looking just like C vector looked. If you got a million vectors and you add them together, it's going to look like any one of those vectors. Only difference is the components of all the vectors associated with the x direction are all going to be added together for the new x component. All associated with the y direction are going to be added together to give you the new component associated with the resultant vector, and so on and so forth. The new z component is the sum of all the z components. But it looks like a vector. All the vectors at the end of the day, you guys, when you add them, I don't care how big they are, it's looking like this. Heck, I don't know where that came from. That A sub x, it might have been the sum of 5 billion vectors. 5 billion x components. 5 billion x components gave me the grand total of A sub x. Another, then 5 billion y components gave me the grand total of A sub y. 5 billion z components gave me the grand total of A sub z, whatever that is. Yeah, that's what I've been saying. That's what I've been saying. Okay, we know all that. Sorry, guys, I'm running for my eraser. I just don't. These erasers are so large sometimes. I'm going to be knocking them off the shelf here, pretty much. We do this. So what's going on here? We're saying there's got to be a distributive property. Order does matter now. We'll talk. We're going to prove that right there, and then that's going to snowball into everything I just said, but erased. Everything I said and erased. It's going to be this. Yeah, that's what we're claiming. Tell you what. Munham and Foulis, in their brilliant work, say this. If I don't think their work is brilliant, if you don't think that I think their work is brilliant, I don't think I've only said it about 50 times. They say D vector. Why don't you please say that D vector is a vector They're saying that. You guys see something here? I do. What on earth would D vector equal? What on earth would D vector have to equal for this thing right here to be a true statement? What on earth would D vector have to equal? Well, yeah, I mean, take this guy, subtract this guy on each side, and subtract this guy on each side, and that'd be 0. It'd be the 0 vector. This has got to be the 0 vector. If we got to prove it, we got to prove that D vector is the 0 vector. You know what? Munnam and Foulis tell us that it is sufficient, that's to say, it's sufficient to prove that D vector equals the 0 vector. Yeah, every time that's the case, ladies and gentlemen, that's sufficient to prove that the magnitude of D vector is equal to 0. Or the magnitude squared of D vector is equal to 0. Let me kind of say it another way here, guys. If the magnitude of D vector were equal to 0, then the magnitude squared of D vector would be equal to 0. And that's the same as D vector dot D vector is equal to 0. And that's where you need to be. That's where we need to be. D vector dot D vector dot D vector dot D vector is equal to 0. Yeah, that'd be the magnitude squared. Didn't we say that the dot product times the dot product is the magnitude squared? If the magnitude squared is equal to 0, that means the dot product times the dot product is equal to 0. The only way two dot products are going to end up being 0 is if the magnitude of the two vectors. There is no way. The magnitude of the two vectors, of the one vector, there's no two vectors here. The magnitude of this one vector, which is the same vector, it's got to be this. It's got to be this. Okay. So if you can show that, you're good. Here we go. What is D vector dot D vector? D vector dot D vector is, they're kind of slick here. Brilliant. Their work is brilliant. They take D vector and leave it. Leave the D vector written like this. Here's D vector written like this, and then they write D vector on this side for the other one in a different way. But it's still D vector, ladies and gentlemen. Oh, okay. Sounds good to me. Here we go. Didn't we say, now we already proved a lot of stuff about the dot product. You can distribute. You can distribute the dot product. We have been there. We have done that. We have been there. We have done that. So let's go. So what we have here is D vector dot D vector. Let's distribute it. Let's distribute it throughout. Now, if you got a problem with this, guys, minus, everybody understands that minus is the same as plus a negative. Minus is the same as plus a negative 1 times the quantity. So go there if you want. You don't have to. It means the same thing. I can make every subtraction into addition. And therefore, the conclusions earlier drawn are not going to be a problem for us. We have no problem making statements like this since we can convert all subtraction into addition. So what do we got? Let's go. Let's talk a little bit. Let's take this guy. Let's distribute this dot product, ladies and gentlemen. And what we have is correct. Yeah, okay. Yeah, I said that. Let's make a big move here. We got to here. That's a dot product. This is a mess. I'm not lying. I mean, at least it looks like a mess. It's not really a mess, but it kind of looks like one. Plus a negative, plus a negative, plus a negative, plus a negative 1 times that. You can do it like that. Doesn't matter. That's not the point, guys. We're not worried about that. But if we want to be very rigorous, we can do that and make it line up just fine. That's not an issue. We know how to do that. Why is this so important? There's got to be a way out of here. There's got to be something. We spent a lot of time looking at this. How can we make this make a little bit of sense? I got an idea. All of this is valid. They all go, even here you think, what are you talking about? There's something going on right here. Not really. Put A, B, and C in a line and you can start moving stuff around. You got to remember, I can bring A, B, C, I can hook C around up here, and then figure it that way. I mean, there's a lot you can do here, guys. Let me just try to see what we could say. A, C, yeah, there's a lot can be done. Don't worry about that. I wish we had more time, more resources, guys. We'll do the best we can with what we got. This is fine. This is fine. And this is true. Let's look at these two right here. That's very true. It's all true, actually. But let's look at those two. Well, you know what we said. The cross product, the dot product, done the right way, you pick them up and change them. Look at that. Look at that. The dot product, the cross product. Okay. The dot product, the cross product. Pick up the cross product, pick up the dot product, interchange them. Pick them up, interchange dot product and cross product. Or go over here, interchange dot product and cross product. You know what I'm doing? What's going on here? Yeah, be my guest. This is one vector. Don't let it bother you. This is another one vector, and this is another one vector. There's 3 vectors. I just told you, you can have a million of these added together. It still results in one vector. One vector here, the sum is the resultant. The resultant of this is one vector. One vector results. Here's one vector, and here's another one vector. 3 vectors. There's 3 vectors here. Pick up the x, pick up the dot, switch them around. Or pick up the dot, pick up the x, switch them around. You're over here. You know where I'm going. Take a walk. Let's go. You're going to pick up, the cross is going to go over there, the dot's going to go over here. Dot B vector. Now we got to be careful. Who's who? We already said, pick up the dot, pick up the dot, pick up the cross, pick up the dot product, or pick up the symbol for dot product, pick up the symbol for cross product, pick them up and switch them. Sounds good to me. It's going to be D cross A dot the single vector composed of who knows how many things you've added, but it's right there. And you can do the same exact thing for these guys. Here's the minus. Pick them up. D cross A pick them up. Guys, I'm picking up the symbol for cross product, and I'm picking up the symbol for dot product, and I'm reversing their locations. And I'm doing it everywhere I can, having started with this guy. Did I do anything wrong? I hope not. Here's dot, here's cross. Pick up the dot, pick up the cross, move them. The dot and the cross, pick them up, interchange. Dot and cross, pick them up, interchange. Dot and cross, pick them up, interchange. Let me see here. Pick them up, interchange. Looks good. Let me see here. Yeah, it looks pretty good to me. Let me just see really quick, guys, just to make sure everything's okay. It's on the mark. Yeah, it looks good to me. Right. Fantastic. Cross product goes over here. The dot product goes over there. Looks good. Looks excellent. Yeah. Okay. That's important. So what we can say here, right. Now, I'm going to be careful here. I don't know what, hopefully you're comfortably, let me leave that thing up top that I have. Let me erase something now. Let me kind of take my time on this one. Okay, you see what we're doing. I got to talk to you. This right here is important because that's a single vector, as convoluted as it is, and the dot product is distributive. Make a long story short, this guy right here that I just underlined is indeed that. That's one vector, whatever it is. And when you do a dot product, it is distributive. It is distributive. I don't know why I did that. It's not even as legible as it was earlier, but okay, sorry about that. All right. So it's, if you're going to distribute it, you got this plus yes. Minus that's this guy. Okay, well, I think you know where I'm going here. This, let's see here. Same as plus a negative. We've already delivered that speech.
this right here, the magnitude of this and the magnitude of that, they're the same thing as far as what they are. So if you take this and subtract this, so this, subtract the exact same thing from it. If you take that and subtract that same thing from it, proof is complete. Yeah, absolutely. It's pretty fascinating stuff. Pretty fascinating stuff. So we're not going to say let, we're going to say is. Equals 0, which implies A vector cross the sum of these two vectors is equal to A vector cross B vector. Pretty fascinating stuff, guys. Monim and Foulis have a really good way of doing stuff like this and making it make sense. Very well motivated. Old textbook, very well done. Absolutely. So by induction, I mean, there's a lot going on here. By induction, you guys, you can do this with any number of stuff here. And there's so many ways to look at this. The mathematics is beautiful. And I'm not saying that Monim and Foulis were the first guys to do that. I'm sure they weren't. This is raw. I don't know when the cross product came out. It's been around long enough, I'm sure. I mean, very long. Talk about a lot of the great mathematicians. A lot of this stuff, you know, Archimedes, Gauss, Newton, and countless others, known and unknown, from everywhere, from many places. Known and unknown, guys. What's going on here? Yeah, this is a true statement. If you were to do this, by induction, you can take it as far as you want. Take A vector cross the sum here. Let's put another guy in here. D. This is a different D now, guys. I'm making the statement that this right here, and Monim and Foulis talk about this. Okay, I just said something very trivial. Yeah, I'm drawing this conclusion. You guys understand if I do this, I can keep going by induction. Keep going by induction. How does it work? You could take this. You could take A vector cross and take B vector plus C vector as a single vector. I already said it's a single vector. Plus D vector, like that. And that's going to be, I want to prove this. Forgive me, guys. I want to kind of come to here and prove this. So let me kind of
Get some new chalk pretty soon, guys. Right, true. Well, yeah, we already proved this up here. If there's two vectors added together, there's a resultant vector. When you do A vector cross the resultant of the sum of these two vectors, you get A vector cross B vector plus A vector cross C vector. Well, this becomes like your new A vector, and this becomes like this becomes your new B vector, and this becomes your new C vector in a sense. It's the cross product, A vector cross the sum of two vectors is the sum of the cross products. Well, I'm going to call this one vector. I'm going to call this another one vector, and I end up getting this. You say, yeah, true, but not so fast. And I'm going to say, no, I disagree. We can go that fast. Because once you go to here, notice that. You can always tack on the other guy. This is the guy you just tacked on. Yeah, what about this? Yeah, well, what about it? We already drew that conclusion. Yeah, sure works. It sure works. And you can do that again. You could take this big one now. B vector plus C vector plus D vector. That big vector, that's the result of adding B vector plus C vector plus D vector. You could take that guy and call it one vector. That's your new vector A. And then plus a new vector B for the fourth guy. So on and so forth. Goes on indefinitely. Look at it. It happened. Right here was the big move. You took this and you came to here. And that's where that's coming from. So what's going on here? Well, yeah, you know what's going on here. I mean, bottom line is, and you can do this a number of ways. Okay, Mullen and Fullis do it there. You know, they got a different order in how they're going to do this, you guys. But we're not worried about that. We know what we're doing. Is there a moral to the story here? Yeah, I got a moral to the story for you. If you go A vector cross B1 vector plus dot plus B sub n vector. I don't care how many vectors you got. You can have a billion of them. Billion with a B. 5 billion with a B. If you do this, got A vector cross B1 vector plus dot. Oh, forgive me here, guys. Yes, definitely. You know that. By induction, it works. Okay. Okay, what else you want to say? Yeah, well, I'll tell you another way to look at it. What if this was the case? B1 vector plus, let's switch them up. What's that equal to? Hold on. Didn't we say, generally speaking, ladies and gentlemen, the cross product of two vectors equals the opposite of the cross product of the two vectors if you reverse the order of the cross multiplication. In plain English, if you turn this thing around, if you take this and turn it around, you're going to get negative 1 times A vector cross B vector plus dot plus B sub n vector which is going to equal negative A vector cross B1 vector plus negative, let me see how far I'm going to, I'll do what I'm doing here. You know where you get where I'm going, guys. Negative 1 times that, or negative times that, or negative 1 times that. You know the deal. Yeah, true. What else you want to say about that? Well, the opposite of this cross product is simply the non-opposite of this. The opposite of this cross product is just doing the cross product in reverse without putting an opposite on there. The opposite of this cross product is the same as switching these guys around and getting rid of the negative. The opposite of this cross product is this cross product. The opposite of this cross product is this. Well, yeah, that's pretty fascinating. Yeah, you're looking right at it. You're looking right at it. What happens is, okay. Pretty fascinating stuff. Yeah, absolutely. Absolutely true. Now what? So many ways to go, you know. What you're gonna do, let's see what else I wanted to say on this. Again, I go into this, guys. You're gonna have it on paper too. You already, those of you who have me right now in the classes that I'm teaching, you have it on paper. You have it on Canvas. Wasn't able to get all this transferred to film, but I mean, it's on Canvas for those of you that want to look at it there. In this particular case, I'll have it on film as well, right at the end of all this discussion. It's all on film. You know, we can rather easily use the last two conclusions regarding the distributive property for the cross product for the very general conclusion of what the cross product is, and which we already mentioned. And we can look at it. You know, equals what we said, and it can be expressed in other ways here. So let me, there's a lot of looks here, guys. Again, I'm jumping around a little bit with the order here. Let me see what I can say here. So we said this. Okay. Is there a real general conclusion we can draw? Yeah, I mean, see what we're going to say here, guys. When we look at this thing, I think I looked at it a bunch of ways here. Let me leave some of that. Let me get rid of some of the other stuff. In terms of where you're going to go with this stuff, guys. Yeah, I mean, it's pretty easy move. Actually, it's just a little bit on the tedious side. But let's see what we can do here, guys. Let me just take some of this stuff out of here. So again, the conclusions are very old. Exactly when this stuff was coming out, you guys, I don't know, but they're old. I mean, before Munham and Foulis and before myself, and been around a long time, and just fascinating stuff what they're able to do with the mathematics. Okay, so let's draw a general conclusion here and see what we can say here, guys. We said where we can draw conclusions. I mean, there's some conclusions that can be drawn, and we're going to actually make, I'm trying to just arguing with myself here where I want to draw, how I want to draw these conclusions. Man, I wish I could just bring the board up that I had earlier, right? We're going to just do it again. Give me 1 second, guys. I'm a little short on the chalk here. Let's talk. Well, you remember the earlier conclusion, guys. We're making the claim that at the end of the day, when this thing, or at least a lot of the conclusions we have been drawing, what if you had, and we talked about the whole thing here. Forgive me for showing you again, but sometimes repetition is the mother of learning. That's M, that's M, that's N, and we have said you're going to draw conclusions. It's a lot of ways to go, but you're drawing the same. It's kind of interesting. If you do the distributive principle going this way even, and catching all the, you get the same answer as long as you keep the order the same. I haven't really said that. There's only so much you can say sometimes, guys, but there's a lot of equal answers you're going to get no matter how you approach this, as long as your mathematics is sound. For our purposes, I tell you what I'm going to do. What do you say you look at this and you look at all the conclusions we drew, because these big conclusions that we've come up with right here, guys, are pretty important. Very important. Because they're true, that thing to the far left is also true, because they're true. So it's pretty fascinating stuff that way, guys. Because they're true. So, tell you what I'm going to do. I just said this whole thing is one big vector. That whole thing is one big vector, you guys. That thing I just put in parentheses. Heck, if you want to argue it, the other thing is one big vector too. Now, yeah, true. They're both, each one's one big vector. As big as you want to have as a vector. Tell you what I'm going to do. What do you say? This is not the only way to go. It's certainly not the only way to go, but let's go there anyway. What do you say that we... I have so many ways to go. All right. Let's take this. It doesn't matter what I'm about to show you guys. Let's take this. Let's go from the left and go all this and get all of it. What are you talking about here? If you take one big vector, or one small vector, whatever it is. Take one big vector and cross product with all this. One big vector and cross product with all this. That one big vector meets up with each of the items in all this. In the all this, each one of these component vectors will be hit by a vector and go all the way across. What does that mean? Treat this guy as one big vector. We'll call it a vector. We'll call this whole thing a vector, no subscript. A vector, no subscript. What does that mean? It means you got this guy, whatever it is, cross B sub 1 plus the whole thing again. Because this whole guy is one big vector. We're going to call that one big vector a vector. That whole big vector, a1 vector plus a2 vector plus a3 vector plus dot, 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 dot plus a sub n vector, we're going to say that equals a vector. No subscripts. We'll have him come across. Here, comes to there, comes to there, comes to there. Bam, 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 bam. It's that one. All right, treat that whole conglomerate like it's one vector that's coming across and hitting everybody. Cross plus, you know where I'm going. Yeah, true. Great. Now what? Well, I used the first conclusion, so to speak, if you want to call this top one the first conclusion. Now let's use the second conclusion. Here's an individual, and here's a whole bunch of individuals making one individual. Well, the whole bunch of individuals that are going to be in there to do it are going to come out to, it's going to be a little bit of a mess, but it's something we're going to make it happen. So what's going on here, guys? It just goes all the way across. Every one of these is going to meet up with that. And that's just one row. That's one row with m columns, and there's n rows. Depending how you want to write the thing, but I think I wrote it a little differently in the other one. I think, I wrote it somewhat differently. It's not really a big, how the heck did I do that? Yeah, there's going to be n columns, that says, so let me just write it. I'm going to write the way I had it. It's the same exact thing we had earlier, guys. There's not going to be, I'm just going to run out of room is what I'm going to do. But okay, so all of that comes over here. And let's go. So each one of these guys, this is going to be, well, it's a little different. I set it up a little differently. It's the same exact sum, you guys, but it's going to be, it's a horse apiece, guys. It doesn't matter a whole lot. This is going to be m rows and then n columns, where the other one was actually the same. You could also make it m columns and then n rows. It doesn't matter. So the way I wrote it earlier is going to have a different look. It's the same exact items being added together. There's m times n items. M times n items added together, and they're all identical in either case. So you go here. It doesn't matter. I could have done this order first and then gone to here, and it would have been similar to what I had written earlier. It's not a big deal, guys. It's the same exact answer. Now I just want to make sure I write it for you. It's going to look different though. It's going to look a little different, but it's the same items, guaranteed. Let
me just make sure I don't do anything careless here. A sub 1, A sub 2. So I tell you what, let me write it so it looks like the other one, if you don't mind. This is going to be A1 cross B1, A2 cross B2, A3 cross, I'm sorry, A1 cross B1, A2 cross B1, A3 cross B1, AM cross B1. So for that first iteration there, let me write it like this. I'm not even thrilled that I'm writing it like this, but I want to make it look like what was going on earlier. It doesn't matter how you're going to write this down. If you write all M times N items, I'm writing it like this, though I wanted to write it across. It doesn't matter. You could have, you could have M rows. I'm making it M rows, N columns, but I could also have N rows and M columns, as long as all of it's there at this point. Plus. And you'll see it. I'll have the documentation there, guys. You'll have the document in front of you. Right. Okay, that was this one. That got us to here. Now we'll go over here. It's the same business, but it's going to be B2 on this one. So we did all this, and I put them down in a column. I put this result, I put it in a column. So since I'm doing it with columns, let's do that. It's probably better if I put it in rows, but I just wanted to make it look like the other one looked. It doesn't matter, guys. It's the same M times N terms exactly. Their sum is the same. So A1 vector cross B2, A2 vector cross. So everybody, A2 vector cross B2 vector, dot, 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 plus A sub M vector cross B2 vector. Yeah, I mean, it's kind of ugly how I chose to go. I put all of this in the order of column. All of this in a column. All of this in another column. So the first one is this column. First one is this column. Second one is that column. Plus dot, 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 plus, and of course I'm going to run out of room, guys, but I think you know where I'm going. The very end of it, it's going to be this guy, A1 BN on down, A2 BN, A3 BN. So what do we got here? We got A1 cross BN. We got A2 cross BN. Right, and it just stays that way. And cross BN down here. AM AM rather, I'm sorry. Guys, this stuff is easier done than said, and it's easier visualized than said sometimes, but it's looking like this. Okay.
It's exactly what I showed you earlier, how the whole thing's going to play out. We're looking at this thing. So you look at it, what's the deal here at the end of all that? So we got all this. The order that you do it, that's not the big thing. This is huge. You got over there. Let me write it over here, guys. I just think it's easier for you to see it. But you saw what I'm doing. You not only saw what I'm doing, and you didn't have to go here. You could have started with this guy and then go one by one on these guys. Well, that's what that is. That's the second one. You could have started with the second one, drawn a conclusion, then jumped to the first one and drawn the conclusion. You're coming out the same way. When you're looking at this, there's just a little bit more room here, guys, so forgive me here on this. Regardless of how you go, I mean, let me just do this. We got this far, might as well just, I think you can see it a little bit better. And it's worth seeing again, I think. Doesn't matter how you're putting in these particular arguments right here, guys. The way that it's done, just think it's easier. Pluses and dot, 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 dot. Pluses, dot, dot, dot. You guys get the picture. A sub m cross B1 A sub m cross B2 plus dot dot is obviously the third time you're looking at this, guys, but I don't know how legible. I don't like how legible it is, but it's more legible here than it was over there, I think. Hopefully. Either that's your call. I mean, but you know where we're coming from, guys. M rows, N columns. Total. Here's N terms. There's M terms. Total M times N terms. M times N cross products. And that gives you one big. What happens when you add all these cross products together, guys? What happens when you add all these cross products together? When you add all these cross products together, each one of those cross products is a vector. You keep adding all these vectors together, you get one big vector. You get one big vector. That's interesting. Whenever you're adding vectors together, you just get another vector. No more, no less. Kind of like adding numbers. If I add two numbers together, I just get another number. You add two vectors together, I get another vector. So on and so forth, you guys. Well, that's great. Let's kind of stay with these conclusions. This is pretty important stuff. Because then we can go to something kind of relatively major. I mean, in other words, these are very important conclusions. So let's see what we have. Okay. What's so interesting about this? I think there's a lot you could say. There's a lot of ways we can argue what we need to argue. At some point, I gotta opt not to argue it. I think I create more problems for you than I'm gonna solve for you. But we do know that it's an equation, right? And I'd like to say, can we say a couple things here? Do we know a couple things? Can we, I guess what I'm just arguing with myself. I did another way of showing of where you can get exactly to these conclusions. I showed it in another manner. So let me kind of merge the two approaches in a sense, and maybe there's something there, we can talk about. So let's see. Let's see a couple things we can say, and I'd like to kind of I'll try to merge my argument. I'm sure, like I said, I'm sure other people have done this argument before I've done it regarding what I'm going to go into, and you see also the brilliant argument of Munham and Foulis, which was also, I'm sure, done at other times as well. But it doesn't make the argument and the research any less brilliant, you guys. It's good to see that there are great scholars that have looked into this stuff, and it's helping me out. It helps me to do my job because I don't know as much as they know. And they like I said, there's a lot we can learn from this stuff, guys, and we kind of may take our own look at this to make it make sense to us. That's an important thing too when we're doing a lot of this stuff. Okay, well, you saw that. So we know the distributive principle works big time in a whole bunch of different ways, both for the dot product and for the cross product. And that's, again, fascinating stuff. Well, I'll tell you what. Let me do a couple things, and then we'll figure out what we want to say. Okay. Let's see something. Let's talk. Let's verify something, and then let's sort of start from scratch and say, okay, let's look at this another way. Let's draw the same conclusion. We don't have to say everything over, because if we come to certain key conclusions, one very special key conclusion it'll become pretty obvious that we don't need to, because we already proved a lot of the stuff. But we got to reach that key conclusion. Well, we're going to reach that key conclusion right now, and then we're going to reach it in another manner. So I'm trying to marry two techniques here for looking at this. Let's see how this goes. Okay, guys. 1 second here, guys. Make sure this thing's working. Give me 1 second. I gotta. Sorry about that, guys. Just had to hydrate a little bit. Even though I love to talk very much, I mean, it's. All right, guys, let's keep talking. Well, again, this is, to me, really fascinating stuff. We got to talk. I mean, we've got to talk more about the guts of what's going on with this thing. I mean, what do you want to say here? Well, I'll tell you what. You know, you could call C vector, if you want, call C vector A vector cross B vector. A vector, let's make sure, guys, that can be heard. Okay. A vector is AXI hat plus okay, let's write this. Believable. Let's write this. True. Okay. So let's see here. We gotta talk. We proved a lot of stuff. We proved very significantly, you know, there's a lot going on. I mean, we've got the magnitude of A vector cross B vector. Sometimes they don't put two bars like this. You just put one. That's neither here nor there. We've got this thing is the magnitude of A times the magnitude of B times the sine of the angle between the two vectors. Now, I know I called it phi earlier, but I can just easily call it theta. It's not the same theta we used earlier on when we said, oh yeah, the angle between C vector and A vector cross B vector. Here, C vector and A vector cross B vector, first of all, the same thing. I said C vector equals A vector cross B vector, and it's not the angle between the cross product and some other entity that is associated with a volume. It is simply the angle theta now will be the angle between the two vectors. In this case, it'll be, A vector here, B vector there, and now I'm saying theta. So now use the language that theta is that. Earlier, we weren't saying that. Earlier, we were saying this earlier, we just weren't using this language. Okay? And we said this is what it's equal to. And all that beautiful mathematics of what scholars teach us when we look at the stuff, all that beautiful stuff that we're learning from all these scholars, all these mathematicians, when we're looking at it, the stuff that we had just looked at, beautiful mathematics in its own right, we didn't really talk about the magnitude.
of that. We drew conclusions. Actually, we did talk about the magnitude, but what kind of, can we verify it? We actually did. We said AB sine something. AB sine phi. In this case, phi, we're going to say phi equals theta in this case. Theta is going to be that phi. AB sine phi is the magnitude of A vector cross B vector. A vector cross B vector is the magnitude of A times the magnitude of B times the sine of the angle between them. What's the angle? Well, it's phi earlier, or you can call it theta now. Whatever you want to call it, just be consistent with your language. We're consistent, we said that. AB sine theta, AB magnitude of A, the magnitude of A vector, times the magnitude of B vector. What is that? Well, in three-dimensional space, use the quadratic formula to find the magnitude of A vector. Same thing with B vector. The magnitude of B vector, the magnitude of A vector. Magnitude of A vector times the magnitude of B vector times the sine of the angle between them is the magnitude of A vector cross B vector. Pretty fascinating stuff. Tell you what, let me kind of merge in some of the discussion I was saying earlier, and I think we're going to feel pretty good about it. Let's ask a couple questions. According to what we did earlier, A vector cross B vector is equal to A vector cross, well, here's A vector. I just said the sum of all these vectors gives you a mega vector called B vector for the B part. And we did say this, we had AB sine theta, so we'll get there. The sum of all these vectors gives you the mega vector B vector. Yeah, okay. You know the deal, guys. We've been there. Now we got to be careful a little bit. There's a lot that goes on. As we said, A vector cross B vector, if you're finding its magnitude, that's the magnitude of A times the magnitude of B times the sine of the angle between them. Rather than phi this time, let's just call it theta. So it's a different problem, but it's the same exact mathematics, just using a little different language. That's all. If this is so, see what else I want to say here, guys, regarding this. If you've got, what did we say the cross product was, you guys? We said if this is A vector, and this is B vector, and this is theta, you go A vector cross B vector, it goes perpendicular. Magnitude of this times the magnitude of that times the sine of the angle between them. Yeah. What if the vectors lie right on top of each other? Well, I don't care what the magnitude of A is. I don't care what the magnitude of B is. The magnitude of A times the magnitude of B might be something huge. The magnitude of A times the magnitude of B might be something huge. True. What's the sine of the angle between them? What's the angle between the two if they lie on top of each other? If they're both going in the same direction, the angle between them, theta, is equal to 0. What's the sign of 0? It's 0. So when two vectors are right in line with each other, their cross product is 0. When two vectors are oppositely directed from one another, the sign of 180 degrees is also 0. So if they're oppositely, if they go in the exact same direction, or they are oppositely directed from one another, their cross product is 0. If they are perpendicular to each other, here's A vector, here's B vector. You go right-handed orientation, the thumb will point that way. That's a 90-degree angle. What's the sine of 90 degrees? Well, that's the biggest sine value that you're ever going to get. In terms of magnitude, anytime you're getting the sine of 90, or the sine of, any multiple of, the sine of 90, the sine of, go 180 onto that. Anytime you're adding 180 onto that, the sine of 90, the sine of 270, the sine of, looking at it, what would that be? 450, etc. Anytime you're going, anytime you're adding pi radians or 180 degrees, you're going to be getting a magnitude of 1. Sometimes it's going to reverse now. It's going to go, the sine of a particular function is going to be 1. The sine is going to be -1. The sine is going to be 1 again. The sine is going to be negative, whatever. But you are going to get values according to the right-hand rule. All right, there's a lot going on here. There's also this. Let's say you talk about the y component. That's in the I direction. This is in the j direction. And that's the k direction. If you go I cross j, you get k vector. If you go j cross k, you get I vector. If you go, there's a lot that goes on, I guess you could say. Look at the orientation here, guys. This is I hat, j hat, k hat. I cross j is k vector. J cross k is I vector. K cross I is j vector. If you go the other direction, you're getting negative, if you go here. If you go j cross I, you get negative k vector. If you go k cross j, you get negative I vector. If you get, so on and so forth. I'm trying to think of something I didn't hit here. If you go I cross j, you get negative j vector. So on and so forth. But they're all of size 1. I hat, j hat, and k hat. I hat is associated with the x-axis. J hat is associated with the y-axis. K hat is associated with the z-axis. Okay. All right. Well, just wanted to tell you that. And I want this. Not that we need it there. We got it in enough places. But let me try to leave this here somewhere so we can kind of make a transition to something. Transition from Munham and Foulis to some of the stuff I was saying, to some of the stuff I'm sure people long before any of us were saying a lot of this stuff, guys. All right, we do know that the distributive property works in the most general sense. We did that in excruciating detail, so we know it works. We know it works. Let's do it. Let's go. Let's take the a sub x I hat and just go across here. A sub x I hat cross b sub x I hat. A sub x I hat cross b sub y j hat plus
A sub x I hat cross B sub z k hat plus. Guys, I'm taking this and distributing. Look, we know it works in the most general sense. Let's go A sub y. A sub y I hat cross B sub x I hat plus A sub y I hat cross B sub y j hat cross A sub y I hat cross B sub z k hat. Let me just make sure I did that. No, I actually, let me see. Yeah, I'm absolutely wrong. Okay, here's j hat. Okay. So that's good to double check, I guess, right? If I had a live audience, they would have caught me by now. Luckily, I caught it here, right? So let's see what we're doing here. You did the A sub x, you did the A sub x I hat, and you cross product those three items with it, and you got that. Then you took the A sub y j hat, and you cross product all the way across. Let me make sure I can see what I'm doing here. Okay, yeah, it looks pretty good. Looks all right. I'm not seeing anything now. Okay. A sub z k hat. And here we go. A sub z k hat, cross product with this. A sub z k hat, cross product with this. And A sub z k hat yeah, that's true. Look, we did this in excruciating detail to prove I don't care how many vectors you got that are composing the first, I don't care how many vectors you got that you're adding together which compose the first big vector, and I don't care how many vectors you got which you're adding together, which are composing the second big vector. The distributive property in the most general sense holds. We just proved it. With Munham and Fullis's great research and great writing on the topic, we proved it. So we got it to here. Great. Man, that's a mess. I mean, it's a mess, but it's true. Can we make that true mess look easier to look at? Yeah, I mean, when things lie right on top of each other, these two vectors are going in the I direction. Those two vectors are going in the I direction, you guys. And if they're going in the same direction, the cross product of two things going in the same direction is a zero vector. These two guys are going in the same direction, both going in the j direction associated with the y-axis. So either in the same direction or diametrically opposite directions. They could be going diametrically opposite to each other too. Don't get me wrong. Same direction or diameter. So k vector, j vector, I vector. It's out of there. It's out of there. It's going to be, when you do this, the cross product is going to be. Another thing you got to talk about cross products, guys. They just become, if you had a constant, okay, let's talk. If you had a constant times a vector and you're crossing it with b vector, that's the same as the constant times the end result of just a vector cross b vector. And that's the same as the c can go anywhere there. In other words, if you had, let's say, you had a constant a scalar, cross B, B vector like that. That's the same as A times B times the cross product of A vector cross B vector. The multiplication of it would be this. This wouldn't take away from the direction. This wouldn't take away from this. The direction is determined by vector quantities, you guys. Direction is determined by vector quantities. Now if this was a negative, yeah, okay, a negative number, it's going to reverse it. Yeah, I get all that. It's going to reverse it, but the size of the vector ain't going to change. The size of the vector doesn't change. If you got like a vector looking like this, and then like this, whatever the result of that, the resultant vector looking like this, if you were to somehow take it and have this guy going the other direction, for that, let's just see here. Right. Trying to see exactly how I would do this. Let me just talk to you because this kind of came up here, guys. I want to, if we made it this far, let's see why it's actually the case. So if we the actual size of vectors here. Oh, you're not adding them, you're doing cross products. So that's why I was kind of running into trouble here. We're going to make that statement, and we're going to say this as well, you guys. I just want to kind of prove to you why this is coming out the way it is. What you can do is if you had, like I said, you had a vector here, and it was doing this, and you had another vector here, and this was A vector, this was B vector, and this is theta. Magnitude of this times magnitude of this times the sine of theta. If you were going to go this way instead, this right here is 180 minus theta. 180 minus theta is the same size sine function as the other one. It may have a different, if this was, let's take this guy, let's say this was negative, let's say this was negative A or something like that, you know. The sine of 180, the sine of the quantity 180 minus theta, and the sine of the quantity theta. The sine of theta is something. The sine of, between 0 and, let's say, 180 or something like that. And let's make the degrees that way. Let's not worry about the 360 and stuff because there's probably a number of ways we could do it. But we could also stay 0 and 180 for our purposes right now. The sine of theta that's to 180. If this is theta, right here, this right here, from here to here, this right here is 180 minus theta. Well, and it's theta away from here. So it's theta from here and theta from there because of the symmetry, guys. The sine, I don't know what's legible, guys. I'm worried about the film, if you can see me. The sine of 180 minus theta equals the sine of theta, always. So, what's the magnitude of the cross product? It's magnitude of A times magnitude of B, magnitude of A times magnitude of B, times the sine of the angle between them. Here, it'd be magnitude of negative A, which is still A, the same size as A, and the magnitude of B, which is still the same size as B. So A and B are the same, and the sine of 180 minus theta is the same thing. So you get the same answer if you multiply by a negative or not. Now, how do you get the same answer when the numbers are actually bigger? If you made this guy right here, let's just say you started with a vector that was really small, and now you got small a scalar, times a vector, and this one is, we're not worried, we just said the negatives don't create a problem, right? As far as magnitude is concerned. If you actually did the cross product comes out, the cross product this way comes out the board. Bring this guy this way, then do the cross, here you did it, do the cross product, thumb comes out the board. Put the A in this direction, cross product goes in the board, but it's the same magnitude. All right. What if this is A times A and this is B times this? What's going on here? It's still going to be, depending on the signs now. Let's say the signs aren't different. The signs aren't going to change the direction, the orientation. We already said the sizes aren't going to change. Okay? For a given scenario, if you put a negative in front, you can make that a negative A, you can make that a negative B and a negative A right here, and it still goes. If you do this, it has the exact same, so look at this. Here's that, here's that, here's that, here's that, here's that, do a cross product. That's crazy. Take this guy, take small a times a vector, take small b times b vector, small a times a vector, small b times b vector, do the cross product, comes out the exact same direction as these came out before they were there. Yeah, sure do. How big are they? This vector now is a times bigger than it was before. This vector here is b times bigger than it was before. So however big this guy was, when you put a small a here and a small b here, this was a times bigger than it was earlier. This one's b times bigger than it was earlier. So if you multiply two magnitudes, one being a times bigger than it was before, and the other one being b times bigger than it was before, a times b the size. So the vector will have the exact same direction, but it'll have the exact same direction as a, and we said that here. Look, cross product, it comes out the same way as it always did. It comes out the same way it always did, but if you put a small a right here and a small b right here, it's, yeah, I mean, you look at it, if you had small a here, small b here, that becomes small a times a. The size of small a vector, the size of small a times a vector is the size of a vector times a. The size of small b times b vector is the size of b vector times b. The sine of the angle between them was theta. This thing's AB times big A, big B sine theta. It's AB bigger. It's AB bigger. So that's why these cross products are going to play out like that, guys. Forgive the big digression there, but I thought, just in case, you don't think we're making this up. All right, you guys, we're saying this. I think we know a lot. This stuff, there's no end to what we can say with this stuff. It's one of the frustrating things about mathematics, and it's one of the great beautiful things about mathematics, the great challenge, the great beauty of it as well. Let's look at this and figure out what we're going to do regarding that. Get a little more chalk, you guys. What do we got? Well, okay, I delivered that speech for a reason. Scalar, scalar, vector, vector. I vector cross j vector. And again, we got it here somewhere. We got it. Here's k vector. Here is, let's put I, we can put I vector this way if you want. Here's I vector. Here's J vector. Here's K vector. Let's just do the job here, guys. Start going. I vector cross J vector is K vector. I vector cross J vector is K vector. AX times BY, I vector cross J vector, I vector cross J vector is K vector. I think I erased something I shouldn't have erased here. I had no room, guys. Let me see here. AXI, BZ, K vector. Okay. All right, well, we'll talk about it right now. All right, we got this guy. AX, BZ. AX, BZ. All right, sounds good to me. AX, BZ. Again, there was a reason I delivered, there was a reason for that huge digression. There was a reason for that huge digression, guys, so this stuff is not too bad for us. AX, BZ, I cross K, roll the fingers, right hand. I cross K, boom. That's negative J. It's not going to this guy. I cross K, that's negative J. That's negative J. All right, negative J, I'll leave the negative right there. Let's go over here. J cross I. J cross I. J cross I. Okay, right hand. J cross I, downward. That's negative K. So it's plus J cross I, huh? J cross I is negative K. AY BX. That's negative K. J cross I. Right hand, roll. Roll the right hand, thumb goes down. That's negative K. Sorry, guys, going to be multicolored chalk here, but that's all right. That's what I usually do anyway, right? See what we got here. Might as well. I'm going to go somewhere else here. I'm going to go right here. You'll see why in a second. Doesn't matter as long as I get everything right. K vector cross I vector. K vector cross I vector. It's positive J. Okay. That's a positive J. All right. That was a negative right here. Negative right here. K vector cross I vector, AZ BX. K vector cross I vector, positive J. And that is AZ BX. Okay, did that on purpose. You'll see where I'm coming from. Let's go here. K vector cross J vector. K vector cross J vector. Let me see here. Let me roll. K vector cross J vector. It's negative I. Negative I, huh? K vector cross J vector, that's AZ BY. Let's go J cross K. J cross K is positive I. Wait a minute, I did something wrong here. Let me make sure, let's do this again. K vector cross J vector, K vector cross J vector is negative I. K vector cross J vector is negative I. There's your negative I. A ZBY is in front because of the argument I gave earlier. J, K. J cross K. Here's J, here's K, let's go. Here's J, here's K. J cross K, that's positive I. AYBZ, positive I. That's neat. That's neat. Look at it. It's a mess, but look at it. That's how it works. We got to talk. We definitely got to talk. There it is. So you said this. Well, I don't know. There's got to be a way we can put these down and figure out what we're doing here. Yeah, true story. We got to talk a little bit, I think. I want you to look at something here. For each one of these, there's a negative and a positive associated with the K vector. There's a negative and a positive associated with the J vector. And there's a negative and a positive associated with the I vector. Associated with the I hat, there's a negative and a positive. Associated with the J hat, there's a negative and a positive. Associated with the K hat, there's a negative and a positive. Not only that, look at the subscripts. AXBY K hat. If you take AXBY K hat, if you take the X and put it by the B, and if you take the X associated with the A and put it by the B, and take the Y and put it by the A, if you just take the subscripts X and Y, take the subscripts X and Y and reverse them, the subscripts X and Y and reverse them, you got what's associated, more or less they go together. Here's the K hat. If you take the subscripts X and Z and reverse them, you got this going together. Take the subscripts Z and Y and reverse them, put whatever was by the Z that was by the A, put it by the B. The Y that was by the B, put it by the A. That same kind of logic throughout this whole thing. Just reverse the subscripts and they kind of go together. Yeah, it's a true story. I guess there's a lot of ways you can write this. But we need to talk. I mean, you got the whole thing here. You figured out what this was. That's C vector. The whole thing here, guys. Let me try to make this thing make some sense. Again, I don't like erasing any of it. I mean, if it were up to me, I'd have boards in every single room on this floor, I guess you could say, right? We'd film that way, I guess. But like I said, that's kind of I just forget the fact that you guys have access to be able to reverse this stuff and look at it again if you deem that it's necessary and worthwhile. Okay, guys? So we're looking at this. We're answering a lot of questions. So we got this. Try to think here, man. Let me try to think. I want to make this make sense to you. If you look at all those additions right there, guys. There's a reason I'm going to do this. There's a reason why I'm going to do it. And then we're going to see what we can say about it. We're dealing with this. We're dealing with the C vector, the whole thing. I get it. Do you guys mind, after this song and dance that I just said, we draw a conclusion? We not only draw a conclusion, I'm going to write those, if you don't mind, because the I's go together. How do they go together? Well, here's positive number, sort of. I don't know who's positive and who's negative, so that's a hard thing to say positive and negative. I could say there's a negative number in front of something. I could say there's a negative symbol in front of that, whatever. So you understand that. So I forgive that ambiguity in the language, I guess you could say, non-specificity in the language in a sense. Can we write this down, guys? I'll tell you what, and I'm going to write it in a particular way, and you're going to see why I'm going to write it in a particular way. This is AYBZ, and this is negative AZBY. Okay? You're going to forgive me on this. I'm going to put the negative on. There's a reason I'm doing this. You're going to see in a second. For the J right here, I'm going to write it. I need to have a negative AXBZ. Yeah, I put a negative in front of it. A negative AXBZ means a positive AXBZ, and then throw the negative on it. It's okay. Negative of a negative is going to be positive, and that's this guy, AZBX. You'll see why I'm doing this. Notice how the Z got put in front of the A, the X got put in front of the B. And the other one I'm going to leave alone. I'm going to kind of say, hey, it's like, Malus, what are you doing? I mean, Jim, why are you doing this? I mean, you did it here, and now all of a sudden you want to switch gears on me, you put a negative 1 in front. There's a positive 1, there's a positive 1 in front of this guy, and a negative 1 in front of this guy, and there's another positive 1 here, you're going to see. Because there's a little memory trick that's going to help you out. AXBY right? AXBY minus AXBY AYBX. These are all orthogonal to each other because they're perpendicular. All these vectors are perpendicular to each other. And you add them together, you do a vector sum, and you get to where you want to go. By the way, this is the cross product, ladies and gentlemen, for two vectors with these coordinates. I exploited the cross product multiplication, so to speak. I exploited what the cross product is. I exploited the reality that the cross product is distributive, and I got this pretty fascinating conclusion. So far, so good. Well, you know what the vectors look like, guys. I'm gonna, I can't put everything on. I can't leave everything on the board. I wish I could. I mean it. It's pretty important stuff. Why the heck did I even write it like this? Because they've got this really fascinating mnematic device, memory device. It's from a Greek word. Mnemi is memory. Mnemi. A lot of cognitive terms have that sound, the M and the N to it. I think, like even in Russian, when they say to remember something, or understand something, pomnit, and there's an M and an N there. In Greek, it's there too, mnemi. So it's not. I think it's perhaps not uncommon in some of the Indo-European languages when you see that.
A pneumatic device is a memory trick in a sense, something to help us do it. Look at this thing. What's going on here? Well, look at it carefully. If you were to take and write it, okay, why did I just do, okay, that's fine. Actually, that's fine. I hat, J hat, give me the determinant of this quantity. If you were to reverse the rows, you'll reverse the sign. Hey, wait a minute. When you reverse the multiplication, if you go A cross B, that's the same as negative B cross A. B cross A is the opposite of A cross B. And if you reverse the rows on this, you're going to get opposite sign as well. Evaluate that determinant. This is why I put the negative here. We're going to evaluate by minors and figure out, look, let's make a long story short. Start at I vector. I vector is located in the first row. Use what you know about determinants. I vector is located in the first row, first column. Row number plus column number, 1 and 1 is 2. If it's even, if you get an even number, it's positive. The final coefficient that you're going to have in front is going to be positive, positive 1. You're really taking the quantity negative 1 and you're exponentiating it to the quantity m plus n. Row number plus column number. An even natural number, when you exponentiate negative 1 to an even natural number, you get positive 1. If you exponentiate the quantity negative 1 to an even natural number, you get positive 1. If you exponentiate the quantity negative 1 to an odd natural number, you get negative 1. That's where they're kind of getting it. Shortcut is, if it's even, if the sum is even, you leave it as plus. If the sum is odd, you leave it as negative. This is easier done than said. My language isn't the best here, guys. Let's talk about I. What's associated with the I hat? Associated with the I hat. Associated with the I hat, row 1, column 1. Row 1, column 1. 1 and 1 is 2. It's even. That's plus. Here's the I hat. Cross out this column, cross out that row, and now just do this. Evaluate right here by minors. AY BZ minus BY. AYBZ minus AZBY. AYBZ minus AZBY. AYBZ minus AZBY. So you went here and here. Row number and column number. Add row number is 1, column number is 1. Add row number and column number. 1 and 1 is 2. Even, leave it as is. AYBZ minus AZBY. AYBZ minus AZBY. Or minus BYAZ. It doesn't really matter. Okay, so AYBZ minus AZBY. Now let's go here to this guy, J. Row number, column number. Row number 1, column number 2. 1 and 2 is 3. 3 is odd. The quantity negative 1 to the 3 is negative 1. It's going to be a negative 1 in front. Row number, column number 3. It's going to be negative in front. Cross this out, cross that out. AXBZ minus AZBX. AXBZ minus AXBZ minus AZBX. True, and then a negative in front. So AXBZ minus AZBX, and it's a negative because row number and column number was 3. Go to K.
row number 1, column number 3. 1 and 3 is 4. It's going to be even. AXBY minus AYBX. AXBY minus AYBX. K vector. Fascinating. How did it happen again? Let's do it real quick. I hat is going to be the, I guess you could call it the lead term or the trailing term, but it's going to be something. I hat is the one you're talking about. The big vector, so the vector, the thing that calls the vector a vector, that calls the vector the quantity is the one you go to. Oh, I hat. Oh, this is going to be associated with I hat. This is associated with I hat. Row 1, column 1, 1 and 1 is 2, even. AYBZ minus AZBY. I hat. Row 1, column 2, 1 and 2 is 3. The quantity -1 to the positive 3 is -1, or it's just an odd number, as we said. The J is going to be, there's going to be a negative in front of all this. Okay, let's go. Cross it out here, cross it out there. AXBZ minus AZ, AXBZ minus AZBX. Yeah, it's a negative J. It's a negative. That's going to be working with that. Go here, row number 1, column number 3. 1 and 3, 4, even. Cross it out, cross it out. AXBY, going to be even. That's going to be for the K vector. That's associated with K vector. AXBY minus AYBX. Period. This is a little memory. It's easier than remembering this. If you just write the components of A vector right here and the components of, if you just write the components of A vector right here and the components of B vector right there. Here's I vector, J vector, K vector. The components of A vector are associated with A vector. The components of B vector right there are associated with B vector. And you get this. That's crazy. Is that something else? Well, essentially what happens, you guys, so much to say here, guys. We've got this. It's a little memory. Now I got to make this clear. I think that we've already made it clear, but let's make it very, very clear. This is what we did when we used the fact that we knew that the cross product was generally a distributive phenomenon in the most general sense. If A vector is composed of if A vector is composed of M vectors all added together. So if I take M vectors all added together and call that one big vector, and I take N vectors all added together for another quantity and call that B vector. A vector cross B vector, we get an answer. If I take any M vectors in three-dimensional space and add them together and cross product that entire sum with another entire sum composed generally of the sum of N vectors all added together. If I cross product those two sums, the distributive principle generally works. We've been there. We've done that. We did that with this to get A vector cross B vector. And when we did A vector cross B vector, you guys, A vector, given this was what it was. When they give you this stuff, this is what it was. When they gave you that, then this right here excuse me, guys. Is all this. Yeah, we did it. You saw me do the general application of the distributive property concerning the cross product, and I got that answer when I cross product these two sums. This A vector is a sum of these three vectors. This B vector is a sum of these three vectors, and I did a general application of the cross product. I did a general application of the distributive principle. I did a general application of the distributive principle concerning the cross product of two sums. where the vectors are involved in three-dimensional space. A cross product of two sums. And it worked. I got it. I got this answer. And like I said, the memory trick is nice. This works. Absolutely it works. Know that like you know your name, guys. It works good. It works good. Let me... All right. Absolutely. Absolutely. I got some questions to ask you. It doesn't, it's kind of neat. This is true. This is just a true story, generally speaking. Now let's shift gears a little bit. Let me not go into it. I don't know how greatly I want to go into it. I did it in there's different ways we can do that. Let me just say something here, guys. Okay, this is true, important, everything's good. Got a couple questions to ask you. How big is that answer? We already claimed. I mean, there's a lot of questions I got to ask you, I guess. Well, here's one of them. How big is this? How big is this answer? Well, I already know how big the answer is. It's the magnitude of the cross product is the magnitude of A. The magnitude of the cross product of two vectors. I know the vectors obey the right-hand rule as to where they're going to go. At least that's the claim I'm making. But the magnitude of the cross product is the magnitude of A vector, which is a scalar. I didn't put a vector symbol here because it's the magnitude of A vector. Didn't put a vector symbol here because it's a scalar. The magnitude of the cross product of two vectors, A vector cross B vector, is A vector, the magnitude of A vector cross B vector is the magnitude of A times the magnitude of B times the sine of theta. Yeah, if you say so. It's its own interesting question. Let's believe that's true. Let's believe that's true, but before we go there, let me kind of mention something and kind of just maybe leave it. What if, I want to see, do you remember the conclusions we drew earlier? I'm probably not going to be able to write it down for a third or fourth time, but we got it in our notes, we got it on the film. We remember what the cross product was of the sum of something. Cross product, what's the cross product of the sum of a bunch of vectors crossed, what's the cross product of a bunch of vectors added together, that sum cross product with the sum of a bunch of other vectors added together? And we say, yeah, we knew what that was, Jim. I'm going to stay here for 1 second. I'm going to ask you a question. This is done, the done deal. This is true. It holds for this, but man, let's go general on this. Let's kind of look at this perhaps in another fashion. Can I say to you, do you mind if I call A vector equal to A1 vector plus A2 vector plus dot 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 plus A sub n, A sub m vector? I'm giving them different names now. B vector is B sub 1 vector plus B sub 2 vector plus dot 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 plus B sub n vector. Okay. Each one, I think I got, I can't, I'm not seeing it here, guys. I know I have it somewhere in here. somewhere. I'm not seeing it here, guys, but I know we'll have it. Yeah, right. I do have it. That's what I thought. Yeah, right. It's on some of the later pages. Let's write it like that. Okay, when we know, okay, we said what we said. This is true. You know where it generally works. Could I ask you a question? Can you make, let's now still call AX vector equal to all this. Let's call A vector equal to all these. And let's call them equal to all these. But now you got to be, now let's say something about it. Let's make, for example, let's make B sub x vector. Let's take this guy right here. There is a B sub x quantity. And the B sub x is the x component of this guy plus the x component of that guy plus dot, 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 dot plus the x component of that guy. In other words, the first guy, his x component, added with the second guy's x component plus dot, dot, dot plus the nth guy's x component. That's B sub x. That's the new B sub x. Same stuff. But now I'm making it bigger. I'm making it the product, the big stuff right now. And see what we can do here. And we could say that A, let me see. Let me try to find it here. Then we could say that period. That'd be it for the x component. The y component, B1, give me the y value of the B1 vector. Give me the y value of the B2 vector. Give me the y value of that vector. The BZ. You're still going to put I hat, J hat, K hat. B1Z plus B2Z. Give me the Z component from each of these. Wow, yeah, it's all these together though. That's a mess, but yeah, it's what it is. Is what it is. For the A's, okay, let me see here. Just no room, guys. Okay, but you guys got it on film, so I can always go back. You're gonna do the exact same thing for the X's. So what are we doing here? Let's get this straight. Let's get this straight. Let's make this make a little bit of sense. You see that BX right here? Let's make it work that way. You see that BX? BX is composed of n x components. Why are there n x components added together? Because the B vector is the sum of B1 vector, B2 vector, dot 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 plus, B1 vector plus B2 vector plus dot 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 plus B sub n vector. N vectors added together is what B vector is. I'm going to get each x component. I'm going to get the x component from B1, then the x component from B2, then the x component from Bn. I'm going to add all the x components together and I got a big Bx. I'm going to do the same thing with the y component from here, add those together. Add that with the z components. I'm going to take all these x's, and right here I can just kind of put them in, I can put them where Bx is, but I can put them as a sum. Right here. There's only 3 rows and only 3 columns, guys. That doesn't change. Bx right here, you're going to write it small or write it some way or write this really big, but you're going to have, what are you going to have here? You're going to have B1, You're going to have B1, you're going to have this. B1x, B2x, B1x, B2x, B3x, BNX. B1y, B2y, B3y, added together here to get this guy. There's going to be n terms here. If I'm going to write them downward in a column, and that means there's going to be n rows. You're going to come over here, and in place of that, you're going to put, let me see if I can write it. I think you guys know where I'm going here. Problem is, I don't know where I'm going. Okay, let's see. I'm just kidding. I think I got it. I mean, we got this. Now put that. AX, AY, AZ. And let's see here. I think you guys see what I'm doing. A1. Now this one's got M of them. I think, remember, the one had M of them. M. That's all. Not a big deal. Not a big deal. If I can't write, it's a big deal, but let me, hopefully I can. You put in this plate, make it small. There's only 3 rows. This never changes. Remember this. None of this is going to change. I'm just trying to show you some of the power of the mathematics, guys. There is row 1, row 2, row 3. Column 1, column 2, column 3. This is a 3 by 3 determinant. It never changes. Don't ever forget that. You will put in place of B sub x, B1x, B2x, B3x, B4x, B1x, B1x plus B2x, plus B3, B1x plus B2x plus B3x plus plus B sub n x. Remember, we said the B had n of them. So let me know where to write the stuff, guys. You got it on film though. We go back, we got the other one. What the heck, guys? B sub n. N items. B1x plus B1x, B2x, B3x, BNX. Add them all together. That's your BX. B1y, B2y, B3y plus plus B sub ny. Add them all together. That's your BY. B1z, B2z, B3z plus BNZ. Add them all together. That's your that. What you can do is you can write them as a row. You kind of write it kind of weird. You could kind of say, okay, I can put the sums together. Let me kind of do something. Let me sort of create a row within the row, but it's still just one row. B1x, B1y, B2y. Row 1. Row within a row. B1y, B1x, B1y, B1z. B2x, B2y, B2z. B3x, B3y, B3z. Add them. And all those rows are added together. I'm going to tell you why. You can kind of construct it as 3 columns and then n rows. Up here, you do the same thing. A1x, A1y, A2y. A2x, A2y, A2Z. A1X, A1Y, A1Z. A2X, A2Y, A2Z. A3X, A3Y, A3Z, dot, dot, dot. A sub MX, A sub MY, A sub MZ. M rows. Well, yeah, but they're all added. It's weird how you can do it. You can make them into rows, but in reality, here's the weird thing. You got all these rows here, but in reality, this is the AX. What's the AX? The AX is A1X, A2X, A3X, dot, 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 A sub M, X. This one's A1Y, A2Y, A3Y, A4Y, A sub MY. This is A1Z, A2Z, A3Z, AMZ. You add all those together and you got what AX is. You add those M items, add these M items together. Add these M items together. Well, not these. Add these M items together, you've got the AX. If you add these together. You add these together, you got the AY. You add these together, you got the AZ. Yeah. Well, what you can do is you can also pretend they're rows afterwards. But what happens is it's the exact same answer, ladies and gentlemen. You end up getting this, but whoa, man, this is huge. Right here, what do I got? Well, I got a lot going on. I got whatever the sum of the AYs were. What was that? Well, what were the AYs? Well, it was A1Y plus A2Y plus A3Y plus A4Y all the way plus dot 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 A sub MY. This one's what? It's all the sum of the BZs. What's that? That's BZ1, BZ2, BZ3 plus dot 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 plus BZN. The whole thing. Well, how is this going to work out? How on earth can they get? I mean, that's a lot. If you actually put the stuff in there, you know what I'm saying? This is composed of, for lack of a better way to, I don't know about components, but it's composed of M items, they're M Y items that are added together. This is composed of N Z items that are together. This is composed of M as in mom, Z items that are together. This is composed of N as in Nancy, Y items that are together. So, God, what are you doing? This was a lot easier, I guess. It's the same process. Here's what happens, though. When it's like this, you guys, when it's like this, you're basically everybody lines up relatively well. There's going to be a multiplication that takes place here. What do you mean? Well, there's M as in mom items, N as in Nancy items here. When you add them, there's going to be M times N terms. This is going to be M times N terms. This is going to be M times N terms. It's going to be a lot. True. And the way we know it's going to work is we got to make sure that every one of those multiplications is going to take place. Are you kidding me? I mean, you're telling me there's going to be M as in mom terms here, N as in Nancy terms here. M times N is M times N terms. M times N many determinants. How do you get M times N many determinants? If you break up what's here, the multiplication that is taking place here, guys, is you're essentially going, let me see here how we can actually look at this. So we looked at that. Let me kind of just try to quickly do it. It's going to be really hard to reasonably do this, guys, in the time frame that I got. And so I'm already taking a lot of time on this, obviously. But what they're trying to say, you guys, okay, it's the same stuff we talked about. I had to erase something, guys. every one of these corresponds. Let's put it this way. There's an A here, an A here. There's an A here, an A here, or some kind of an A. An A here, 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 an A here. And the B's too. If you correspond all these guys the way they should be, you're basically multiplying at the end of that, following all of these. This is really, you could say that if you just put one of these in here. Let me just try to see how I wrote it, guys. There's no real good way to do it, and I don't want to get everybody too worked up on the whole process. I'll kind of tell you this, I guess. If you're gonna say this, A vector cross B vector, well, okay, I mean, this song and dance we've done already. All right, well, yeah, I said that way over there. Okay. Well, if you're doing this, like I was just saying, A1 A1, add from A1 to A sub M, add them together. Add from B1 to B sub N, add them together. And when you do that, let me see, guys, I'm running out of room a little bit. Said this. Let's see here. Don't want to erase any of it, guys. That's what I don't want to do. But they're all close together, guys, but A sub IX, I think I just need more room, guys. You've seen this. Okay, let me erase it, actually. Like I said, we got the rollback feature when we need it. And we can figure it out. Like I said, when we need to cross that bridge, we'll cross that bridge, I guess. I'll leave that on here for now. not at all obvious, guys. Remember I was telling you about the A1X, A2X, A1X, A2X, A1X plus A2X plus A3X plus ... plus A sub M X. Well, this is among all those, and you're just separating them all out. You'll see, I'll talk about it. Probably, the I here is not I hat. It's not an I hat. It's just an I as an index of summation, you guys. J is not a J hat. It's just another index of summation. They don't need to have the same number. Eventually you want to, I'll make this clear. As clear as it can be made clear, I guess. The sum of M times N determinants to get the total, to get A. This thing right here, if you broke up into different vectors, that's how you get this guy. It'd be M times N determinants. To get. Is that crazy? Important. I mean, I'm sorry, guys. I got drawings all over the place, arrows all over the place. What's going on here? What is going on here with this, guys? Yeah. That one determinant can be made into M times N determinants. You can make it the sum of M times N determinants if you break up all that's being added. Wow. Yeah, it's true. It's true because at the end of the day, this is what this does. How many did I have here, guys? How many cross products did I have when this was M as in mom, number of vectors, right? When we said that, I said a lot of stuff, I don't want to keep going over it. And all right, you'd be less thrilled about it. But we already talked about this. That the A vector is going to be, I guess, some vector plus some other vector plus a total of M vectors. The B vector is going to be some vector plus another vector plus ... plus N vectors. Yeah. Didn't we say when you do the cross product, you're going to get well, let's do it. I tell you what. Let's call this guy the I's. Let's call this guy the J's. All right, here's the I's, here's the J's. And we're claiming you're adding these. Yeah, we said you add them. We said that you add them. Well, wait a minute. Didn't we say that the cross product looked like this anyway? The cross product looked like this anyway. Here you're going to have M times N determinants. And M times N cross products. Yeah? M times N cross products. Every one of them, ladies and gentlemen, is a determinant. Every one of them is a determinant. So individually, they'd look like that. Well, what I said earlier, the way that thing was all played out, we had said that this thing, when it, just at this level, man, we said AY BZ, we said, you're right, for the I, right? For the I associated with the I, AYBZ minus AZBY times I hat minus, that's just the rule, right? AXBZ, right? AXBZ, negative here, AXBZ minus AZ AXBY AXBY minus AY AXBY minus AY, let me just make sure I did it. AXBY minus AYBX. Okay, yeah, this is nuts. Every one of those pieces, how many pieces? Yeah, there's M pieces of X's. There's M pieces of Y's. There's M pieces of Z's. A1X, A2X, A3X. M as in mom, pieces of X's. M as in mom, pieces of Y's. M as in mom, pieces of Z's. N as in Nancy, pieces of X's here associated with the B's. Likewise for the Y's, likewise for the Z's. If they're in here, yeah, it's a pretty crazy multiplication going on. At the end of the day, each one of these, you guys, it's not going to get wacky. Each one is M times N products. Also 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 M times N products. And you just line them up according to the vector. This guy right here, there's going to be, of those things going on, for example, there is going to be, I don't know, let's say this guy is B sub 10, X, B sub 10, Y, B sub 10, Z. Okay. A sub 5, X, A sub 5, Y, A sub 5, Z. It'll be in there. It'll occur in the multiplication. There will be like we said, where it was. One of them they'll be here. It will be, and again, you're going across in the row here for what it was, right? For the B, so this would be B5 vector, A5 vector. This would be B10 vector, and you're doing the cross product there. Why is that true? Because there is associated with this guy for each one of these. Now there's associated when the whole multiplication takes place, you guys. There's going to be that the A sub 5, I don't know which one I called 5, I forgot what it was called, 5 or 10. I think this was A sub 5 and this was B sub 10. Doesn't matter, just pick one of them and stay with it. A sub 5, B sub 10. If you plug it in for one of them, in here, the A5 is going to go to the B10. Every single permutation every single combination given this particular look right here. We get into permutations if we're starting to flip this thing around a little bit. But every possible handshake that can take place, there's M times N. There's going to be M times N products with this guy, M times N with that, and you could separate M times N products, 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 M times N products. I got a better idea. Yeah, there's going to be total of that much. This is one of those M times N's. One of those M times N this is one of those M times, a total of M times N determinants. This is one of those M times N determinants. And it's going to work that you're going to have M times N of them. M times N of them, guys, to have it happen. That's crazy. It's crazy, but it's true. It works. It works. It works. Well, that's all great. Okay, great. Here's the thing. It's all right. I mean, it's a good thing. And there's, like I said, different. It's all here, guys. At some level, at least I hope. I hope it's at a decent level for you guys. We got it here. I guess what we got to ask ourselves at the end of all this, does this thing obey the right-hand rule? This vector, does it obey the right-hand rule, and is it perpendicular? Is it perpendicular to both things we ask it to be perpendicular to? And this is kind of where I came in. I'm not going to do given all the time that this has taken. This is a lot of fun, guys. I don't know if you're going to have as much fun looking at this stuff as I am. Hopefully you get somehow familiar with it and just go forward a little bit. Look at it any way you want, I guess, but hopefully it's some benefit to you if you want to look at something like this. At least go forward and come back and stuff like that to parts that might be of interest. Let me not prove it my way very rigorously, but let me more or less do it anyway. Let me give you some of the highlights of it. I guess the big thing that you got to ask in all of this, is this A cross B? Is this A cross B, which we know is equal to this? We proved it's equal to this. My writing's not that great, guys. I was circling and yelling and all that other stuff, but you've seen it. You already got it in your notes. We know how to do it. Is the cross product, does it have a magnitude of AB sine theta? And is it perpendicular to both A and B in a right-handed fashion? I mean, we take guesses to it, and this is kind of the way I proved it. In the end, I kind of took an educated guess at it. I don't know how educated the guess was, but it was a guess. We threw the dice a little bit, and we were actually able to get it. So let me erase this, and let's ask a couple questions. Let's ask, is it all true? Okay, let me come right back to this, guys. Let me come right back to this. I will see you guys in a little bit. Okay, guys, let's finish it up. I'll kind of go into some of the stuff I did when I approached the matter and kind of take an educated guess at it, but I'll more just talk you through that. It is in the literature. If you're taking one of my classes, you'll see all this in Canvas, the learning management system that we have. If not, you're going to see it at the video as it scrolls down. So we drew this conclusion, and a lot of fascinating conclusions come from this conclusion. There's something I guess you got to ask when you're doing something like this. At the end of the day, I mean, we've asked this question and sort of put it off. We've not put it off completely. We've done a lot of stuff to be able to answer a lot of stuff, and it had to be, heck, I mean, the very intuitive argument that Munham and Foulis gave us regarding how to get a lot of conclusions and draw a lot of conclusions, their very intuitive argument really did use the fact that the magnitude of the cross product is the magnitude of A times the magnitude of B times the sine of theta. Now remember, we used a different angle way early on when we talked about this, but that's, I don't know, is that true? Are you going to tell me this thing right? I mean, this is pretty crazy stuff. I guess the questions you got to ask on this, and this is similar to how I proved it. Like I said, I'm probably just going to, given all the time that this is taking, and there's nothing wrong with that. I mean, I hope it's of use to you guys and you want to look at it. You might not want to look at all of it, but maybe bits and pieces of this will make some sense for you. Hopefully all of it makes a lot of sense for you. You want to look at it. But anyway, I'm trying to be very comprehensive about this whole thing. As far as how I approached it, I'll give you some of the arguments around how I approached it. Essentially, it was this. I didn't know this initially. I had to say, all right, I started here. I knew that the magnitude had to be this. If the magnitude had to be this, you would essentially, I guess approach this a whole bunch of ways, I guess you could say. If A vector is, again, we've seen this ad nauseum already, right? I mean, but if you're looking at this, and this is just a straight out single vector. I mean, you can make it composed of a lot of vectors. You saw me make it composed of a lot of vectors. Heck, we had M as in mom and N as in Nancy. The product of M as in mom and N as in Nancy determinants. M times N determinants will give you that very generalized answer for the cross product when it involves M vectors in one grouping and N vectors in the other grouping, and you're doing the cross product of both groupings, I guess you could say. That's a great way to say it. If one sum is composed of M vectors and the other sum is composed of N vectors, the cross product of those two sums is the sum of N times N cross products. It's the sum of M times N determinants. And that's what we said last time that we were together very recently. Okay, with this right here, we're not worried about much else than just saying this. It's single vector here. And then we're saying this. Yeah, okay, we've done this. We've been there. Okay, yeah, great. I'd like to confirm if this is actually true. What is this? What's going on here? I mean, we're saying, is it true? And I showed it in different ways in my thing. Now, like I said, I didn't even necessarily, like I said, I'm starting out the proof without even knowing this. I'm saying, okay, let's define the cross product as being this in terms of magnitude, and in terms of direction, obeying the right-hand rule as far as its orientation. So we know its orientation in terms of the right-hand rule, and we also know its magnitude. We know its orientation by definition according to what the right-hand rule says. So we define the cross product to be associated with that particular orientation and also associated with this kind of a magnitude. Yeah, great. Okay, can we prove it? I mean, can we figure out what the heck's going on? Well, I'll tell you what. Is it true that AB sine theta is equal to, we could say a whole bunch of stuff here, I guess. We could say that it's equal to the square root of, let me try to think here, guys. You could go, how about a squared b squared wait a minute. 1 minus cosine squared theta is sine squared theta. A squared, B squared, sine squared theta, the square root of it gives you that. AB sine theta, is that true? Yeah, it looks good to me. 1 minus cosine squared theta. 1 minus cosine squared theta is sine squared theta. A squared, B squared, sine squared. The square root of A squared, B squared, sine squared is AB sine theta. Got more questions to ask. This is A squared, B squared. And okay, let's distribute it across and see what happens here. Distribute it across. Wait a minute. Isn't A squared, B squared, cosine squared, isn't that A dot B? A times B times cosine. A times B times cosine theta is A dot B. This is A squared, B squared equals this. Yeah, good luck. And like I said, I showed it in my notes. I showed it a little differently. I used different notation rather than the A sub x, A sub y, A sub z, and the B sub x, B sub y, B sub z. I used lowercase a, lowercase b, lowercase c for one of them, and then lowercase x, lowercase y, lowercase z for the other. It just seemed easier because I don't know all the stuff that was going to be going on, man. It was just going to be pretty much all over the place on this thing. Yeah, I guess we can kind of look at it. I mean, there's a number of ways to go here. I'm trying to kind of believe where I'm going too. And again, if we can just get a couple good guesses, we can kill a whole bunch of birds with one stone, I guess you could say. And I'm just trying to argue with myself here, guys. So, we can kind of say a few things. Why don't you square both? Why don't you square both sides? And you end up getting the magnitude of A vector cross B vector squared. That's A squared, B squared, sine squared, which is the same as, and if you square the, so let's just square both sides, guys. Square both sides. And you end up getting, let's figure out what we're getting. We're getting A sub x squared plus A sub y squared plus A sub z squared. That is this guy. I mean, so what you're getting here is let me kind of go there again. You got A cross B. Got A squared, B squared minus A dot B. Well, maybe there's a way to get out of this. I mean, well, here's A squared. Here's B squared in terms of magnitude. And the other one is, that's interesting. We got AX, BX plus AY, BY plus AZ. I hope you guys can see this okay. So I got here. Squared. Okay. So what we got here, guys, and I'm going a little different technique on how I showed it when I did it cold, but this is some of my argument of how I had gone. It's not, I'm sure, and again, guys, I'm sure I'm not the only guy having made this argument. There's no way
at all under any circumstances that has occurred. When you do all this, you end up getting, I mean, it's kind of a lengthy process, and I don't know how much more anybody's going to tolerate looking at me on this particular film, you guys, but if you've stuck it out this far, I really appreciate it. This thing right here is going to be a whole bunch of ways you can actually say it. Let's stay with this. When you actually go here, and again, I use different notation, guys. So let me stay with only, I did this. I stayed with it. I'm going to stay with this notation. So let's see. Let me see how I want to write this. This is pretty fascinating stuff. I got to employ the multinomial theorem at some level right here, and I got to employ what's going on here. Now, look, guys, there's some fascinating stuff about to happen. First of all, the quantity ax bx will end up getting squared. The quantity ay by will end up getting squared, and the quantity az bz will end up getting squared. And even here, ax squared bx squared, that's going to show up. Ay squared by squared is going to show up. Az squared bz squared is going to show up. Those three products are going to get knocked out from three products. Look, here there's going to be nine products summed together. Three of them are going to get pulled out of there. There's going to be 9 products total when you square this. It's going to be pretty complicated, relatively complicated stuff sometimes, but one term, 1, 2, 3, 3 terms. 3 terms are going to be squared. You're going to get a total of 9 terms. 3 of those 9 terms are going to be ax squared bx squared, ay squared by squared, az squared bz squared, and here, of the 9 terms, 3 of them are going to be ax squared bx squared, ay squared by squared, az squared bz squared, so they're gone. You're going to get 6 terms over here and 6 terms over here, and that should be of interest. So what happens, there's a whole bunch of stuff that happens, actually, is what happens, but, and I kind of showed it in my way here when I did it. At the end of the day, you guys, it's going to be a mess, but, I mean, you look at it, let me kind of just get us through this at least. I want to see what this is. And again, we're not forgetting here, this is the cross product squared. This is a squared b squared sine squared theta. So let's see what it is. When you do all this, at the end of the day, you end up getting something like this. Again, I used the stuff I used, man. I just wish I didn't. I use different, now that I got different notation when you guys look at it, okay? Let's see what we got here. The A vector's got that, the B vector's got that. Okay, I think I'll be okay. All right. I got to kind of translate some stuff here. Yeah, this is why I used just single letters when I was first doing this. This is not, forgive me guys, let me erase this. This is not, try to give myself a little bit more room. Tell you what, again, I did use different notation when I did this. I probably should have stayed with that different notation. There's a saying in Greek, bikis to chorotha chorepsis. If you enter a dance, you got to dance. So let me stay with the dance then, I guess you could say. This thing is going to come out to, when you do all this wheeling and dealing here, guys, you are going to find it to be this.
Man, I should have stayed with those single letters, you guys. That's for sure. Okay, but let me just go with it. That's AX. I'm just interpreting here as I go along. BY, I got to translate it to the way we've been using it. I didn't want to play too many games. AY. BX. Okay, let's see what I got here. So we did a lot of stuff, guys. I got to erase some stuff. I'm sorry. Okay, we're using, like I said, sometimes some notation is better than others, I guess you could say. So you go here. All right, guys. It's a lengthy process when you actually do it. I kind of just cut to the chase. It is in the notes. I used notation like that, which I'm not supposed to be using now. Bear with me, guys. So let's try that again. All right, forgive me, guys. It was, I think, an easier setup before, but okay. There's a lot that's got to get done, and man, it already looks like something, man. It already looks like it. Let's see here. Yeah, it's if you're careful here, man, it's already there. Now, again, a lot went into getting that. It wasn't anything that was incredibly difficult to do conceptually, but very tedious. If you grind out the polynomial, the multiplication of polynomials, if you grind out the multiplication of polynomials, you're going to get that answer, and then just evaluate what it is. Well, yeah, that's pretty significant. There's a lot I don't know. I mean, I don't know who's where. I don't know what's associated with the I vector, technically, let's say, if I'm doing this cold. What's associated with the I hat? What's associated with the J hat? What's associated with the K hat? Let's purposely, I guess you could say. Okay, we got this. We're making this claim, and this is what it is. So let's just confirm it. I mean, let me kind of cut to the chase, guys, a little bit. It's not exactly the way I want to do it now, but given all the other stuff that we've done, I think we've really got the background that we need, to be honest with you. And you do have my literature to read if you choose to do so, and it'll scroll at the end of the video. What's going on here? I mean, I guess we've got, at the end of the day, we've got the magnitude of A vector. The magnitude of A vector cross B vector squared is the same as A vector cross B vector, whatever result that is, dotted with A vector cross B vector. Oh, really? Yeah, that's the X components, the Y components. So there's a lot they can be identical. Remember, it can be like AX BX
plus AYBY plus AZBZ. AXBX plus AYBY plus AZBZ. So I want to look at it. Yeah, I want to look at it, and I want to kind of make it look like something, if you don't mind. We got an AYZ. There's a Y and a Z and a Y. An A and a Y. Let's see here. Let's just make sure we got it here, guys. There's AY. Yeah, there's the top guy. AYBZ. AYBZ minus AZBY. Oh, okay. Are you telling me if I took AY, I'm going a little different than what I showed, guys. I'm just kind of trying to cut to the chase here. You can look at my literature in a little more detail if you want, how the argument proceeds. But let me argue this with you, if you don't mind. That's I hat. Let me call it I hat. It's here. Just follow. Just trust me. There's an AXBZ. Yeah, there's an AXBZ, and there's an AZBX. Wow, it's right there. Okay, if you don't mind. I'm gonna call that a nav. I'm gonna make it look like that. You're gonna see what I'm doing in a second. Yeah. Okay. What did we do here? We had the AYBZ business. The AYBZ business, the AXBZ business, the AXBY, that's the K, the AXBY, AYBX. Well, it's the same stuff, man. It looks, well, that's a lot. That's significant. So AXBY, not making it up, guys. You just saw it. AXBY. Okay, let's see here. And for some reason, I can't see what I just wrote. There it is. AXBY, AYBX. Yeah, I know. We know. We know this. We know this. We know a lot pertaining to this, and this is some crazy, beautiful conclusions that we can draw related to it. We know all this. We know this, we just don't know how big that is. Yeah, well, I tell you what, we now do. We know this is true. Well, we know this is true assuming we know the magnitude. We didn't really go against. It's a fascinating argument, guys. I can tell you that for sure. This is consistent with the magnitude. This is consistent with what takes place when you find the magnitude of a three-dimensional parallelepiped. When you find the magnitude of the volume of when you find the magnitude of the volume of a three-dimensional parallelepiped, some sort of box either sheared over to the side or no matter, some sort of box in three-dimensional space, it can be sheared over to the side, of course, but some sort of box in three-dimensional space, when you find its volume, you're using the cross products. We found all that stuff out. Man, I believe all that, and it all works. We were able to draw a lot of conclusions. The distributive property, done in so many different ways, in so many diverse ways, the distributive property generally is, as we applied the distributive property generally, wow, that was some great conclusions. Still, I'd like to confirm that, what's going on with that thing? There's the vector.
Does it really obey the right-hand rule? Is it perpendicular to both A vector and B vector? And it satisfies the right-hand rule? And it's as big as the magnitude of A vector times the magnitude, and it's as big as the magnitude of A vector times the magnitude of B vector times the sine of the angle between them. I tell you what, I already defined, we already defined this. We already said, if you're going to take A vector cross B vector, by definition, the magnitude of that was the square root of the quantity A squared, B squared times sine squared, and sine squared was this. We played games with this, and we said, wait a minute, isn't that A squared, B squared minus A squared, B squared cosine theta? Didn't we say that was A squared, B squared minus A dot B? I'm sorry, cosine squared theta. That's the cosine, it's got to be cosine squared. A dot B squared. If you square both sides, AB sine theta, if it is AB sine theta, the magnitude of A, if you've got a magnitude AB sine theta, when you square it, you're going to have this. You're going to have this. Okay. Ladies and gentlemen, I'd like to find out what this is. I'd like to find out what this is. Yeah, you just did. It's that. You're telling me the magnitude of the cross product squared is equal to that. That's the same as finding the magnitude of this vector. Because this is the magnitude of the cross product squared is equal to this, which is equal to all that. If you take this vector, which you propose to be the cross product, if you square each component, you will get the square of the magnitude of the vector. Well, the square of the magnitude of this vector, if you square this component and add it to the square of that component, get rid of the I vector, the J vector, the K vector. How do you do that? We'll go this vector dot this vector. The cross product dotted with the same exact cross product is the magnitude of the cross product squared. If this is the cross product, we propose that it is. We say that it is according to everything there. If this is the cross product, the magnitude of this cross product is this component squared, the scalar associate, the length of this component squared, the length of this component squared, and the length of this component squared, all added together, then square rooted. If you square the square root of the quantity, you just have the quantity itself. Basically, the magnitude of this component is simply this. The magnitude of this component is simply this. Magnitude of this component is simply that. Magnitude of this component is simply that. If you square all of the components and add them together, that is equal to the square of the cross product. Really. Squaring each component and adding them together is the square of the cross product. Yeah, I started out with the assumption that the cross product had to be the product AB sine theta squared. The product AB sine theta squared is indeed this, which is identical. The square of the cross product is the quantity AB sine theta squared, which is equal to all this. The magnitude of this vector is identical to that. If you square root each side here, this is the length of the vector. If you square root all of this having been squared, that'll be the same length of the vector. Guys, it's the same vector. If you're here and you're dotting it with here, J vector, ax, by. If you do a dot product here, you're just going this guy times this guy. Well, this guy dot with this guy, I vector dot I vector is 1. This times this is one of these guys squared. Do a dot product here. Remember, it goes ax bx, ay by, az bz. You know, ax bx, ay by, az bz, ax bx, ay by, az bz. What does that mean? It really just means all of this squared. All of that squared. All of that squared and add them together. Get rid of the I, get rid of the J, get rid of the K. Take this, square it. Take this, square it. Take this, square it. What does that equal to? That's equal to the square of the cross product. Yeah, the square of the cross product was all this. These are the same numbers. These are the same numbers. Remember here, the negative times the negative is going to be positive. It's going to come out of there. It's not going to be a problem. The negative and the negative, I mean, I'm orienting the vectors in different places. When you do the dot product, it's the same thing. AB sine theta, the quantity AB sine theta squared is what this is equal to when you square it. What does that mean? It means when you square root it, the magnitude of the vector is the square root of, it's the square root of the product, a squared b squared sine squared theta. The square root of that product is AB sine theta. That's how big that vector is. Good. Does it obey the right-hand rule? Yeah, it will, because if you take this and you dot it, there's a lot going on. Just give me a little shorter version of this thing, guys, so we can finish this. But like I said, I'll just say a few things in closing. This essentially, what I'm erasing right now, is what I did when I tried to do my version of the proof. I started with the size of the vector, and then I said, well, let me get a vector. Let's see how big the vector is. Let me get a vector. Let's see what its size is. And now let me just kind of experiment and find out which one of those vectors will give me a dot product with a vector that's equal to 0, and that'll give me a dot product with b vector that's equal to 0. And when they're both equal to 0, I say, well, that's the vector. Well, it might be a vector going up, or it might be a vector going down. Which one of those two? There's only two vectors that will make that work. Which one obeys the right-hand rule? Then I just plugged in this. I plugged in I vector cross, I vector cross j vector is k vector. I vector cross j vector is k vector. J vector cross k vector is I vector, and k vector cross I vector is j vector. I plug that. I plug that into here. I took, like I said, I took for here to make it work. I took this AX, whatever. You could say, I just basically said this. A vector was equal to 1 I hat plus 0 j hat plus 0 k hat. And I crossed it, that's the I thing. Then I went 0 I hat plus 1 j hat. I crossed j. 0 k hat. And you can plug those. 1 I hat is just 1. 0 j hat is just 0. 0 k hat is just 0. 0 I hat is 0. 1 j hat is just 1. And 0 k hat is just 0. And then do that, and that'll spit out. That'll spit out k vector. It'll spit out 1 k vector. You could also put it here. What was A? We could say 1 x equals 1 is the only guy that's there. Let me see, nothing here. Nothing here, nothing. X equals 1 is the only guy here. The A sub x is 1, A sub y is 0, A sub z is 0. Okay, that makes 0. This is 1. The z is 0. The z with the b is 0. This is 0. So let's see here. What was it? It was the y. That's just 0. A ain't even in there. This was 0. This was 0. This is 1. This is also 1. 1 times 1 is 1. The y component of the A is 0. The x component of the B is 0. 1 times 1 is 1. 1 times k. Oh, 1 times k, when I plugged it in there, and I did arguments similar to that to prove that it would work. Because I found another one that was negative up here, positive here, and negative here. I multiplied all this by -1, and I was still getting the same magnitude, the right magnitude. It was perpendicular to both A vector and B vector, but it pointed in the quote-unquote wrong direction. It pointed in a left-handed manner. And when you plug the stuff in there, when you went I cross J, you weren't getting K, you were getting negative K. So you knew it wouldn't work. That's basically how I went about trying to solve it when I tried to talk about it. So that's some of the argument there when we actually are looking at something like this. Now, just for the record, is that was I'm sorry, I sort of jumped ahead on that one, showing you how you're going to look at it. But the big thing is, it is as big as a squared b squared sine squared theta. If you square this and add it, get rid of the i's, j's, and k's. Just give me the size of the vector. The size of the vector is this thing independent of this vector. This whole thing, not counting the I hat and etc., not counting the other hats. This thing, not counting the hats. This thing squared plus this thing squared plus this thing squared. The square root of it is indeed magnitude of A times magnitude of B times the sine of theta. You saw me do it. I started with that argument. When I was doing it to kind of make my guess, trying to kind of think here, which one would work. I looked at as many, and I took a couple guesses. There was about maybe on the order of about, this thing was showing up in all kinds of forms. You could have gotten a plus or minus here, a plus or minus here, and a plus or minus here. Well, that's 2 options, 2 options, 2 options. 2 times 2 times 2, 2 to the third is 8 options. In addition to that, these can be rearranged in 6 different ways, 3 factorial ways. 6 times 8, 48. There were 48 ways to maybe take a decent guess. You're not guaranteed it's going to be right. Now, there's an infinite amount of vectors that reach the edge of a sphere that are the size of the radius of the sphere, that are as big as, in this case, AB sine theta. I found two that satisfied the fact that it was orthogonal to both. Only two vectors are going to be orthogonal in three-dimensional space to A vector and B vector simultaneously and have that length. But that length could be a whole lot more. So I took a lot of guesses. The guess I took was something on this order, and that's how I solved it. And once I solved it, and not me, not like I did anything big here. People long before I was doing this stuff were solving this anyway. But my rediscovery of it, just for myself, was I got to here. When I got to here, I found that this was the answer, and it's always the answer. If this is always the answer, then here you can start playing games again. Here you can start playing games again. If this is the answer here, there's a whole lot you can do. You can start tinkering with this stuff. I can switch the rows and get A vector cross B vector is equal to negative B vector cross A vector. B vector cross A vector is the opposite of A vector cross B vector. Put another way, I can put a lot of rows within the row, even though I'm not changing the row. There's only 3 rows. Said that last time. Only 3 columns. I can just construct a huge conglomeration of items within this row and a huge conglomeration of items within this row. This works. And you can break up all the different items that are there. How many are there? M times n. There's going to be m times m determinants that'll satisfy. So you can draw the conclusions that way. One thing that that's what it is. Now, another thing to ask. We just saw that it works to this. Can we get the dot product to work? Can you take this mess, and let me just shorten it up right now, guys. You take this mess, this big mess right here. Take this mess right here and take it and go A vector cross B vector. Well, you know what it is. Again, I've delivered the speech countless times by now. It's this. Take that thing right there and do the dot product with A. Do the dot product with A. Kind of an interesting situation in that regard, I guess you could say. Just trying to figure out how I want to say this. There's a lot of looks at it here. You take that thing, or you can take the other, and take this dot B vector. And I don't want it, let's not, when you do this, you got 0. When you do this, you got 0. You're going to take your guess of this or about 48 other things that are reasonable guesses. None of them might work. I threw the dice and I lucked out. I threw the dice and I just said, okay, let me try a few of these. I said, let's take the 6 of these. There's a lot. Like I said, guys, you could go plus or minus up here, plus or minus up here, and plus or minus up here. That's 8 ways to look at it. And then you can pick up this magnitude and put it associated with I hat. Take what's associated with I hat and put it here, what's associated with K hat. Move them around, you can do that 6 different ways. 8 times 6 is 48. I took a guess and it worked out. And then from there, I was able to draw a lot of conclusions. From there, I could draw some conclusions. Munham and Follis went about it a different way. Their way's better. Their way's definitely better than mine. However, at some point, you've got to go something along the lines of what I'm doing and what other people have done long before me. You've got to go along the lines and figure out how big is this vector. Does it satisfy the fact, if I square this, add them together and get the square root, is that consistent with the mathematics that you just saw me do? Is that consistent with the fact that the magnitude of the vector, A vector cross B vector, is indeed magnitude of B, is indeed magnitude of A times magnitude of B times the sine of theta. The magnitude of A vector cross B vector, that magnitude squared is A squared B squared times sine squared theta. So if you square root it, you get the magnitude. Yeah, all of that said, we already did it. Again, I didn't go through like some of the real tedious work associated with where you're going to do. I already did on paper. You can look at it and verify that this stuff is not a lie. It works out. It works out. And there's a lot of looks we can take on this thing. Trying to figure out where we would actually go. I mean, to look at it, but it works. It works good. Okay, we could be more rigorous on this if we needed to. Okay, but that is it. I'm going to leave it at that. And thank you. Good luck to you in any endeavor that you are pursuing, and I appreciate it. Appreciate all your time. Take care. Bye now.